on. We are planning to release FAQs, like newsletter or some book we are planning. And I request all Bangalore Value Association members to send any questions in DCF for any FAQs you have. We will send a Google form. You can fill in that and we will try to give the answer, and it will be useful for future valuers also, where they will get some doubts about like beta, total beta, or whether we need to take company specific premium, when we need to take, and what are other website we can check. Maybe you people can put all those things, okay, in the Google form, which is helpful for us to prepare some answers, and we will publish the same into our group. Anyone is having questions on this, like what, or like about FAQs, how you need to send it?
No question, please go ahead. Good morning.
Yeah, we shall go ahead now.
Yes, Shilpa, you can start with introduction of today's speaker.
Good morning, everyone. It's my privilege to introduce today's speaker. As all of you are aware, Mr. Ganesh Remani is our Bangalore Valuers Association member. He's a registered valuer, insolvency professional, and practicing advocate enrolled with Bar Council of Maharashtra and Goa, with over 2.5 decades of work experience spread over from entrepreneurship to being an integral part of driving business turnarounds and incubation of new businesses in diverse sectors of finance, technology, retail, and real estate businesses. He is the founder of Enlighten Consultants that specializes in evaluation of new business opportunities, incubation of new business, mergers and acquisitions, and business turnarounds. He is also the founder of a health and fitness startup, KaleFit. Over to you, Mr. Ganesh. In fact, the subject of Monte Carlo is so confusing and difficult. I had requested Mr. Ganesh Remani, after our last session, that please make it little, simpler and easier for us to understand and the practical implications. And I'm thankful to Mr. Ganesh for having accepted our BVA invitation. Over to you, sir.
Thank you so much, Shilpa. Good morning, everyone. You all need to pardon me a little if my voice is not at its best shape, because the last couple of days I've been having slight throat pain and some kind of a painkillers, but otherwise I'm fine. Today's topic is very interesting, not only for you, for me as well. This is one topic which is, I always say that when someone wants to scare the other person, they just say, like a traditional Sholay movie, beta gabbar aa jayega if you don't sleep. Similarly, if someone wants to scare you, they'll just use the word, do you know Monte Carlo techniques? And most of us, at least, will take a back foot because the sheer name of Monte Carlo and what it takes, simulations, there's a little scare. So I started going in as much as possible, because as Shilpa said, it is not easy, or it was never told in simplistic terms. So one is, I shall be attempting to make it simple. That's an attempt. The outcome would be whether you all would agree whether it was simple or not post the session. Secondly, I wanted to ask, a couple of you can definitely mute now, is how many of you are maths background and have heard or used some kind of a Monte Carlo? That would help me to set the expectations right.
I think it is you have asked two questions, and the answers to both questions could be different.
Okay, so let's start with it.
So you could be a maths and stats graduate but not used it.
Okay, how many of you are maths and stats grads? Subaraidu, I could see.
I have.
Fantastic.
Everyone can also respond on the chat also.
It will just help me because one is when I was decided that to take this up, it was a struggle for me how much to bring in maths and not maths. Okay, I could see no maths. Yes, you said no maths gone. Okay. Honestly speaking, the kind of maths involved behind the scenes, majority of us will fall under the category of no only. I'm an engineer myself, and except for some basic terminology, the maths behind this is definitely a little complex. So having said that, we are all finance grads now, and our purpose is for finance and business planning. Thank you so much for the responses. Okay, I would like only top 3 or 5 specific expectations from this session. I'll know whether I'm meeting that or not right upfront myself, which I will not say. Just tell me specific expectations, what you're expecting from this session. End of the session, say we complete in 1.5 hours, 1 hour, 45 minutes. Can you please put in a chat box the specific expectation, what you have come today for this session? Easy to understand, Carlo. Okay, that's one. When it can be used, excellent. Application of Monte Carlo better, number 3. When to use, okay. Application, easy to use. When to use, okay. Alternates of MC method, okay. Where to use this technique and how, okay, when to use it. Some examples, okay. Logic, okay. Good. How to build assumptions, okay. That's relatively, okay. Practical cases, yes. So the title itself says practical, right? So what I did is in this presentation, so that we will see whether we are meeting up to this presentation requirement. I see, fantastic. Thanks for the responses. That would help me. To get fear of not knowing MC method. Can you see the screen? Not yet, right?
Not yet.
Not yet. Okay, one second. How do I share this? Share screen. Share screen. Desktop. Can you see my screen now? No.
Yes.
Yes, we can.
Yes, we can.
Thank you. That is my screen. Okay. So I am trying to set my expectations right up front. And we'll see whether we try to meet this end of the sessions. When I started reading on this as much as possible to give a presentation, I realized that this session can even take 1 full day easily. So then we need to do it in 1.5 hours. So I tried to limit it under these boundaries. This is more of a practical session only, not much of theory. But I shall assure you that the first 30 minutes, probably, I will attempt to bore you by a little bit of theory because you have no choice but to understand the foundation. Once your session is over, you will be familiarized definitely to attempt practically this Monte Carlo simulation. Someone has said practically. Yes, I'm confident, hopefully. The theory part that I'm going to do, one will understand that data distribution is critical, that you will understand the criticality, but you will not have developed really good understanding. But it will help you to read again any other topics behind it for practical experience. That much I believe. I am not covering all the data distribution because there are very many complex ones. What are primarily useful for finance, I have covered it. For business planning, there are more data interpretations, data distributions, but that is something not being covered within 2 hours. Why we need to do? So someone asked me why we should do a MC Monte Carlo is more of a simulation. It's something I'll try to narrate it in our conversations continuously. And some are being covered. So this is the expectation for this session. And based on the chat responses, I see most of this fall around this, nothing outside this. So first of all, I would sincerely like to acknowledge that all the material that I'm presenting below is from various sources available in the public domain. And I would like to specially acknowledge Professor Aswad Damodaran, Professor Nicholas Vittal, and Excel's Fun YouTube videos for me to be able to structure my presentation. So what I'm doing is not something that I have tried to do. I try to pull up a case, put something, my own some data points, but the premise is using the publicly available information. The attempt is to make it simpler for understanding. How do I shift this? Okay. One, you asked why we need Monte Carlo. That's the first question someone asked in the chat box. Please understand, most of us as valuers and also certain business professionals in our day-to-day life, when someone says, okay, what's the sales growth expected? We expect 20% per annum is a growth that we expect. Industry growth rate is around 18-20%. We expect it to grow at 20%. What will be the terminal value? Terminal value we expect around to be 5 to 6%. We know 5% because that is the GDP growth rate. So most of the time, we say a particular number. What happens is, I ask another person, I said, okay, what is your expectation? They may have a slightly say, no, it's not 20%, it can be around 18%. Someone can be say 22%. Now we start having different estimates from different people. Then I'll ask this question, each one of them who has given different answers, what's your confidence to tell me this number? How confident are you? You said 20%, right? How confident are you to get 20%? 100%? Then the people will start saying, no, not 100%. Probably I am 80% confident, 20% confident. This is the confidence that we talk about. Why do we say, we started with a point estimate that this is the growth rate. And the moment we say, what is the confidence that you have it, we suddenly start fumbling upon and give a range now. And this is what we typically call, in easy parlance in Excel, a scenario analysis or a what if analysis. We typically say, I take this number, low number, high number, I see what the number, I get a range. I say, therefore, I am between 18% growth rate to 22% growth rate. So I take three numbers, 18, 20, 22, see the what if analysis, I get some output, and then I say, out of this, I'll take an average. That's the typical way we all do it, right? What happens in businesses when they are critical and some of these decisions can change the valuation significantly, or the manager or the management wants to take a business decision with confidence. Can you tell me with 75% confidence that you are better in taking this decision? What is the risk for me? What is the potential loss that I can incur by taking this business decision? I understand that you are giving me this growth rate. What is the potential loss that I'll incur? How do we do that? So imagine today we went to 3 people and asked 3 different projections. If I were to ask 2,000 people, and based on that, I decide. So the entire uncertainty is because each one gives me a different data point. Okay. How do we actually come with a particular range to make my own business decision? That is when Monte Carlo is used technique. Whenever there is an uncertainty, that uncertainty does not allow me to, the uncertainty might be as simple as, will my profit be more than, say, $10 million? Will my potential loss probability is less than 10%? Because even though I'm making profits based on projections, if my risk appetite is not there, then I may not beyond 10%. And if my potential loss in that decision, while the profitability is very high, is more than 10%, I say I may not be interested in the proposal at all. So this Monte Carlo technique helps us to simulate a particular scenario as if it is done over a large number of times and give us a confidence level. And that is exactly why a Monte Carlo technique is very comfortable to use it. There is a reason behind this. Earlier Monte Carlo technique, even today, in Excel we can do it, but you can do only a limited number of simulations. You have this software, Crystal Ball or At Risk, where that can run multiple times easily. And that's a software, obviously. It has a database around and it can pull up. So prior to some years back, people did not have this power of computers. So they used to use this point estimates. What Mr. Ramadan called as point estimate is a specific number. At 20%, let me predict what's the number. At 18%, they're never able to simulate a large number of times. It also helps in business planning big time, because if you are an employee, you are going for a job and they are offering you ESOPs. There is a particular pattern of the company. And they said that, hey, listen, Ganesh, you will be given ESOPs if you, of so-and-so if you are able to achieve such and such turnover in year 1 or year 3, or such and such profitability. Now, you need to make a call. What's the confidence level that you're going to achieve based on the pattern of the history the company can achieve on various terms? And if the probability that you will be achieving such numbers for you will be able to benefit from ESOPs is say 80%, 75%, you might actually take the risk. But if that comes to only 25%, then you might be better off asking for the fixed income than ESOPs. So, and vice versa for the management to make the plan. So these entire simulations are actually used for such kind of uncertainties in real world. So when someone asks this question, remember, whenever there's an uncertainty where you want to make a call to determine what confidence you have in achieving certain numbers, that is when Monte Carlo is used. If there's a certainty, it's not required. And that uncertainty, how you put it in various boxes, we're going to see that. Hope I covered the very first part, why or when Monte Carlo to be used as a technique. And our session would have questions anytime in between. I'll also moderate it if I believe that time is being crossed. Please do not wait till the last for asking the question. So, as we said, historically and most frequently, we build around point estimates made with the data that we have at the point of estimation. As I said, a specific percentage or a growth rate or attrition rate, so on. But actually what we are saying that this is the growth rate, internally we are all calculating within ourselves that that is the most likely number that's going to come in the potential value. So it is nothing but a mean. So what we did is, when someone asks you what is the estimated growth rate, internally we have made our own estimates. Will it be 17, 18, 19, 20, 21, 22? And then we said, no, it should be the average of 20. And then we are saying, okay, most likely 20 is the number. That's nothing but the mean. We have made a distribution of all these data points in our own estimates. And we said the value that we are saying is nothing but the expected value based on yourself. Knowing fully well that there's a possibility of an error, that what we said as 20 can also be a 17, can also be a 22, because that is something other numbers we have felt it internally, but we made only a final value. We said the point estimates were used because we don't have computer power to do it, but today we have those power because of computer advanced, a lot of advanced computers are there, and Microsoft Excel helps also to a certain extent. I have used the word distribution. So then I felt that let me give you the definition or what the purpose of a distribution. And I think I should name here Shilpa. Shilpa said the moment the word distribution comes up, she actually switches off her mind and switches off her computer. So let me simplify it. Data distribution is nothing but suppose we are in a BVA today, right now, we have around audience of around 65 audience here. Now, this 65 audience is actually classified, various age groups, various academic profile. So for simplistic purpose, if I say that we are in the age group between 30 to say 55. So I can classify it into 30 to 35, 35 to 40, so on and so forth, and put number of people under each bucket. This is nothing but data distribution. You are grouping under a particular category and putting a number, and that is how you have distributed this large amount of 65 people into various buckets of 4 or 5. While I'm presenting, I may not be in the best control of seeing all the time the chart, but yeah, I'm monitoring so that in case I'm not missing the questions. So data distribution, whenever someone says that in a simplistic form, you are trying to group under a particular category. It could be as simple as a binary category of male or a female, heads or a tails in a coin, or in a group of class by age group, you just classify with a range of 30 to 35, 35 to 40, so on and so forth. That classification is nothing but data distribution. Now, what is probabilistic data distribution? Probabilistic data distribution is nothing but, if I were to say that in this particular group, a 30 to 35 number is around 10 people out of 65 people, I can say probably the probability of the audience falling in the age group of 30 to 35 is 10 divided by 65. That's probabilistic data. So you identify probabilities for each age group, and that gives you the rate. Why do we need that probability? Because if we were to expand this, that if this 65 audience tomorrow becomes 650, and day 650 follows the same distribution of the 65 students, I can estimate the number of people in the age group of 30 to 35. It's as simple as that. So why do we distribute? We distribute it to understand where they fall. And if some other distribution, something else follows this exact distribution what we have, we can actually use probability to estimate that. And why do we need that kind of estimation? We will come into it when we look at inventory. Suppose there's a warehouse. We are valuers, right? We have 1 lakh pieces of material over there, and the person has to go and value 1 lakh pieces. He's not going to start counting each piece, right? It's not possible. It's not practically possible. Then he will make an estimate. Okay, I will take a sample out of this entire thing. I group them. So I take a sample of 100, I group them and identify the condition of that particular product and make a condition that it's in a bad shape, partially bad shape, good shape, very good shape, so on. And I'll make a sample out of this 100, how many are falling. And I make an estimate of a probability saying that 10% fall in a very bad shape, or 15% fall in a good shape. So by doing that, now I'm in a control of, if this sample were to be the representative sample of this entire 1 lakh pieces of population, I know how many are in bad shape or how many are in good shape. And that's how every time it's done. Sensex, how do you count the population of country using sample, using this distribution? I hope, Shilpa, have not scared you the word distribution after this.
Yes, I'm getting it.
So here I've given a simple example here. Suppose if you toss a coin 3 times. So we know that the coin all 3 times can be heads, all 3 times it can be tails, 1 time head, 2 time tails, so on and so forth. So this entire audience of these outcomes, which we said here, there are totally 8 outcomes. I'm not getting the mathematics of how many outcomes. It's a simple number. I made it here. So we have a probability which says that no heads at all means all 3 times we get tails as an outcome is 1/8 probability. Similarly, all 3 times heads coming in by flipping coin 3 times is 1/8, and the rest is in between. So we have classified the probability for the simple heads coming out or tails coming out. Histogram is a very popular way of depicting the distribution. because histogram typically what it does is in mathematics, it's a simple class, we call it a class interval. So when I said the age group between 30 to 35, 35 to 40, 40 to 45, that each is a class interval. So that's how it is used. We don't need to worry. We just call it a grouping. And histogram is the most popular way. So we understood data distributions. Then what is standardized data distributions? Now, standardized data distributions is nothing but there's a lot of research happening and a lot of experts sitting around there. And they said that they have predefined certain categories like a normal distribution, binomial distribution, Poisson distribution. So they've already said if a particular pattern is like this, then this can be called as a normal distribution, which is a bell-shaped curve. We understand. If it follows a binary discrete, it's called a binomial distribution. Now, why those are standard distributions? Because if a particular pattern follows the distribution, I have a ready-made solutions, I can use it. This is like in valuations. What we do in valuing a particular property, we look at where can I find the solutions. So, okay, that particular property got sold at this particular price. My property falls in that particular area. So it becomes easy for me. I use the same rate and multiply in my case. Right? We do that, right? So this is exactly the same in data distributions. When there are standard data distributions are available, I just have to apply those properties in my distribution. If that distribution tells me that the average will be 30% of whatever population, I take the 30%, put it in my distribution and use it. That's all standardized data distributions are advantages. So we don't need to do this class intervals, do everything, just look for a ready solution. So as valuers, we are only concerned about standardized data distributions. So our emphasis should be to understand the problem statement that we get in is what data distribution it follows. That's why we are learning these data distributions. Once we know that, then we just have to plug in the ready properties and apply it in our case and take out the output. So we have two kinds of standardized data distributions. One is a discrete or one is a continuous. Now, discrete data distribution takes values discretely, wherein, as I said again, 30 to 35 age bracket, 35 to 40, it's a very discrete. I can count and put in someone there. A continuous data distribution is, it follows in a range. Say, for example, interest rate between 18 to 20%. But it's continuous. It can be 18.12345. It can be 19.374658. I can go to any decimal level and you start counting. It's a continuous between that range. Discrete is where you can actually measure, like age is counted. We can count number of tosses of a coin. We can count 1, 2, 3, 4. It can go to any number. It can go to very large numbers, but we can still count. We can measure it. And a continuous distribution, when the data falls, it's almost impossible to count because it goes to a very difficult detailed level. So we define between a discrete and a continuous. Most of the time, for our valuations, we shall be using continuous distributions. Discrete is also used, but largely. But a discrete distribution is a good use for business assessment, business decision making. A lot of discrete distribution can be done. The other parameter that we are concerned is always symmetric or asymmetric. Now, symmetric is nothing but when I have a data distribution and I have a center of the data, like example, we said, what is the sales growth rate? We said it could be 17, 18, 19, 20, 21, 22, 23, 24, like that. And I said 20 is my mean, for example. I have equal probability on the left side and also on the right side data falling, and that makes it symmetrical. Asymmetric is when I have most likely average is 19, but my low is only on 17, high is on 24. My data distribution is skewed towards the right because my 17 is the low side. I don't have any data point below that. I have a 19, which is my most likely or majority of the data points, but I also on the right side, I can go up to 25. It's asymmetric data distribution. In reality, for us, most of us will struggle for this, and we might actually have an asymmetric data distribution when we are facing. The problem is easier to interpret when it's a symmetric data distribution. That is where, as the valuers, we'll have to make certain assumptions when we are using Monte Carlo techniques. And applying correct data statistical distribution is critical for us to be able to use for our technique. So I will, this is the toughest and most boring part, but just bear with me. I'll try to simplify it before we get on to our model. Deterministic, I'm only introducing this. Directly, it may not have a significance in today's session, but as I said to you, you will have to go back and read a little bit on data distributions, and you will start facing this terminology when you're reading it. And at that time, you might struggle a little bit. So I'm trying to give you an input so that you go back and you'll be familiar and you'll be in a better position to understand. Deterministic model, stochastic model, I put a statement here, but broadly, the concept is simple. In a deterministic model, there's no random variation. So I say, this is the input, this is the output. Take a chemical reaction. Calcium oxide plus carbon dioxide gives calcium carbonate. It doesn't give anything else, right? At a particular temperature. So it's fixed. You give an input, you give an output. That's deterministic model. A stochastic model is, sometimes it can give you calcium carbonate, sometimes it can give you a calcium hydrocarbonate, it can change. If it starts changing, then that's probabilistic. We don't know. So what is the percentage it will give me a calcium carbonate? I start looking at the probabilistic approach. So deterministic is very specific, straightforward, input to output is fixed. A stochastic doesn't give me that specific. There's a variation, there's a randomness in that. I'm introducing to three terms here: random process, random variable, and outcomes, because when you read it, it will come in. Now, what's a random process? Random process is whatever is an experiment that you're doing in. Flipping a coin, that's a random process. What you're doing is a process. It's a steady subject. Counting the population, it's a process. So, or tossing a die, it's a process. So here, the process is nothing but where when you do it, the outcome has to be uncertain. It has to be probabilistic. So if it is not probabilistic, then that's not a random process, because the term itself is a random process, right? So previously we said probabilistic process are random process. Random variation is there. In deterministic, we don't have randomness. So now we are getting gradually into randomness. Random is because there's an uncertainty. Because if there's no uncertainty, there's no Monte Carlo, right? There's no requirement, right? So it's an uncertainty. Uncertainty comes from the randomness. So we are discussing the random process. Given the random process, things can come anytime. So for example, when you flip a coin, it can be head, tail, it can come in. If you try 5 times, it can come 5 different times. Outcome random, the output can vary. Now, what's a random variable? This you have to hear me carefully. Let me first explain the outcome. Outcome as simple in a coin, heads or a tails. Outcome of flipping a dice or rolling a dice in a rise of 6 numbers, 1, 2, 3, 4, 5, 6, any number can come. That's an outcome. The number of 6 or number of 4 when you throw a dice is an outcome. Head or a tail is an outcome. What's the variable here? Variable is when you throw a dice 4 times, what is the probability that my number is 4 all the time? That entire sentence is a random variable. That sentence is a random variable. So what I'm asking is the number 4 appearing all the time, or other variable, the same dice throwing, same number of times I threw the dice, the other variable could be the sum of the numbers which is coming up when I throw a dice is less than 10. That's a variable. That sentence is a variable. Please understand that sentence is a variable. So we now, when I flip a coin 5 times, the number of times heads coming is a variable. The definition is a variable. The sentence is a variable, not different. The sentence is a variable. Now what I'm saying is we are going to say less than or equal to 2. So now I started quantifying it. The number of times heads coming less than or equal to 2 when you throw dice 5 times. Now I completed the entire random variable, and that probability I'm going to estimate. Similarly, I can say rolling a dice, the total value of the number that is coming to me when I throw a dice, the sum of all the numbers is 20 after throwing 10 times the dice. That entire sentence is my random variable. And that you assign a value. So you cannot use such a big sentence, right? So we say X as a value, random variable, and we start saying X less than or equal to 20. 20 is the sum of the value of all the dice. That number is coming up. If heads, we want 3 times out of 5 times we want heads. We say that heads coming in the random variable is less than or equal to 3 or equal to 3. We have put a number to it. That's all. You have to go back and read on this. But I've tried to say that random variable is nothing but a big sentence. We have simplified it by giving an alphabet. Mostly X is used, and then you actually put a value to it. That's random variable. I'll try to give an example here. When you flip a coin, X is a random variable. As I said to you, it's nothing but a full sentence. If the outcome is heads, I'll call it the X, and then I'll give a value equal to 1 if heads come in. If it comes as 0, I'll give it tails. That 1 and 0 need not be 0. It could be any number. I can say X equal to 1000. That's a reference point that 1 and 0 has no meaning. You're actually telling it what is the value that you want. So this is random variable. This part of it for distribution should understand. We will be using the word random variable every time, but you can go back and read it. But it's very simple. A random process, a random variable, and an outcome is it flows one after another, and it's only bringing in the variation. So in our finance world, we can say all these are variables for me: sales growth, selling general administrative expenses, interest rates, terminal growth rate, gross margin. We can have all these as random variables. So we discussed this is similar to discrete distribution and continuous distribution. They actually come from a discrete random variable and a continuous random variable. So discrete random variable is where we can actually count its finite values, and a continuous random variable is not easily counted. It goes from one extreme to the another extreme. In finance, we'll be largely using a continuous random variable because they result in continuous distribution, most likely. So one quick example here, which was interesting for me, and I thought I'll put it here. Suppose exact winning time for 100 meters race to the nearest 100 second. So now here, the moment I said nearest 100 second, I'm defining the second decimal, 9.54, 10.25. So then probably it is countable because it's only 2 decimals. But if I don't give it as 2 decimals, the decimals, humanly it's not possible, but through computers, if it can go to multiple digits, 9.54, 3, 2, 4, 5, 6, 7, as the winning time, it's not possible, then it becomes a continuous distribution. So that was the easiest example here to differentiate between a discrete. So anything which is on decimals, anything which can go to the any level, not from a human eye, from a computer level, then you should call it a continuous distribution. A discrete distribution. So someone asked me, how do I decide what to do it? Largely, you say that if it is very numeric by nature. Let's take an example. My employee attrition, in terms of numbers, I say, every year I have 20 people losing. So I have a definitive number. I can count employees, 20, 25, 30, 100, discrete distribution. If I use a percentages where it can go to any level, then I can actually go for a continuous distribution. So those are the ways to use this when we are trying to do the now the question therefore is, let's come to the next slide. Whenever we are doing a study subject, a data collection, and then data entry, these are the 3-step process, right? So why I'm using this population is, let's take an inventory. As I said to you, a population of 1 lakh pieces of inventory in a warehouse. Okay, I pick up 100 in that. That's a sample, right? So that sample has to be unbiased. That should be a representative of this 1 lakh. Otherwise, valuers, how will you do it? We take a sample and based on that, we make an opinion about it, right? So it should be a representative sample. Now that sample can be collected differently. So for example, sales growth rate, we take time series data. We say that last 5 years, how it has grown. And based on the time series, 5 years, 6 years data, I make an estimate for future. That's a time series because I'm taking over a period of time, how that particular subject matter has varied. Say sales, how did sales grow? Cross-sectional data, the same sales, instead of looking at over a period of time, I can look at over multiple companies. So X company has grown like this. The industry, 5 different companies have grown like this. That's cross-sectional. 1 year, for a particular year, I've taken multiple years now. So now there's a cross-sectional data we can collect on a time series data. So we actually do it all the time. It's just that probably we may not be looking at the terminology. Terminology is so simple. Now, if the sample is unbiased, so now this is critical. So that we always use beta. Technically, it's available. Damodaran has given the beta. How many times have we gone to the sample of companies that he has used in his calculation of beta? That sample may not be at all a representative sample. This, I'll tell you my own experience. We were trying to do shipping industry analysis, and there is a shipping segment in Damodaran's databases, and we quickly went in, okay, we'll use that. And when we saw and we opened up what all companies are there, it had all over the place companies, nothing related to shipping as well. I mean, it's coincidental, we don't know, because he's not going to sit and see every company. He's trying to pull out from various sources of information, and that data is almost of no use. So we have a typical tendency that I have used Damodaran's data. Professor Damodaran obviously is too good, and his data we cannot question at a broad level. Many parameters are of use, but especially when you're trying to do some of this beta or some other data points of his databases, it's important that we need to see, when he said this industry, this data beta is there, you go back and see what all the part are becoming part of it. If majority are representing that, yeah, you're good to go. You can use it. If they are not, the data itself is incorrect. The input is wrong. So we need to know what data we are using it, because the sample is not correct. Whatever error we get because of the bias, the sample that we have considered, that is called as a sampling error. That's called as noise. And that sampling error, we need to do it, fix it. And that is something a valuer has to make some adjustment or judgments. So this, what I'm going to tell now, mostly we all know about it. These are called data descriptives. So when you take a sample, the mean is nothing but the measure of centrality. Where does it fall? So we have a mean, we can do 3 times measure of centrality, mean, median, mode. So we actually know what is a simple arithmetic mean, what is the midpoint, which is also a mean, which is a median here, and mode is what is the most likely to happen. So we have, this is called as measures of centrality. Measures of dispersion, nothing but standard deviation variance. So from the middle, from the mean that I have captured, where is my data falling on each side? That's nothing but standard deviation. That's measures of dispersion. Remember, standard deviation, is it in absolute terms? It also tells you in the same units as the mean. If the mean is, say, in percentages, standard deviation is also in percentages. So when you look at only standard deviation for 2 different entities and comparing it, it could be a serious problem because of the different sizes of the companies. That's when we standardize it, we take it a coefficient of variation. The coefficient of variation, what it does is, it removes the units. Because when I do a standard deviation in value to average value, the units gets nullified and you get an absolute static number. And that number can be applied to all the companies. It does not get impacted because of the size and other parameters. So a standard deviation, whenever you're using it, it should be with respect to the same entity, but you should not compare 2 standard deviations of 2 different entities. That would be incorrect. I hope you got it. And that's why we try to take the ratio. The measures of skewness. Now, I use the word symmetric or asymmetric, right? The skewness is essentially, the data is symmetric, mean, median, mode, everything remains the same. Now, if you were to plot a graph, visualize a graph, if mean, median, mode, if mean is, say, 20%, but median is the midpoint, because midpoint is one we try to bring in symmetry part, then it's at 17%, and most likely that 20%, lowest minimum is around, say, 18%, and maximum is at 25%, but the data is skewed because when I plot a graph, it goes from 18, 20 majority of the points, 25 also have some points, and the data is asymmetric. So skewness actually measures me that. For us, we do not worry as finance values here, but when you're reading about it, it will come in. So skewness will tell me whether distribution is symmetric or not, or asymmetric, and accordingly which data distribution I need to consider. For easy, mostly we tend to do for the symmetric distribution, but we need to be aware of it. What is the error that we are going to give as an outcome when you're doing the valuation or when you're doing the business planning? Extremes. This is something it's too mathematical. It is basically the fat tail. So what happens is when there are data points which also fall very much in the outliers. So for example, I have a mean of 20% with 40% data. I have a 30% data in the outliers at say 14, 15%. Another 30% I have at 25%. My data is actually completely having a lot of fat tails, with 30% of data falling in 14, 15%, 30% in 25, and say majority 40% in falling say 20% in a particular pattern. So as compared to another scenario where 80% data falling at 20%, probably around 10% falling on the left side and 10% falling on the right side. That is a thin tail. So why we are discussing these tails? Because in practice, when we do, if we have a data scattered over, we don't know what to consider. Any data it can fall, right? We don't have a control. So that's an extreme measure. So we should know whether there's a fat tail or a thin tail. And if that is there, then what to do? We need to really think through what parameter will work around. Because this we face, beta is varying. Beta of 10 sample companies, it is going from one extreme of say 1 beta to a 4 beta, or a 0.2 beta to a 3 beta. So then what do? We do a simple average that absolutely is incorrect. And that's the measure of extremes here. The tails are very fat. And standard error. Now, this is a standard error. There's a theorem behind it, and that's why it is we need to know. It is nothing but when I have a standard deviation, I divide it by the number of observation sample under the square root is a formula. What does this tell us? So for example, if I have a standard deviation of 10% and number of observations is 100, I get a standard. This is the error in my estimation of the mean. So if I say that if my sample that I've collected, my mean growth rate of sales is 10%, that's my mean growth rate, fantastic. My standard deviation is 3%. So I have a standard deviation of 3%. Now the sample is 100, right? So therefore the standard error is the 3% standard deviation growth rate divided by square root of 100, which is nothing but 3% by 10. It is 0.3%. That's a standard error. So whatever mean I have calculated, which is a 10%, my population mean, this is a sample mean, my population mean will be different by the standard errors. So the standard error is associated with the mean. So now visualize this as sample size increases. Imagine out of 1 lakh pieces, instead of picking up 100 sample for valuation, I take all 1 lakh pieces. My number of observations in the sample is full. Then my standard error will almost come down because I have completed the entire sample. My population mean and sample mean will be the same because my sample is nothing but equal to the population size. So when I take the sample as small as possible, the error can be much higher. That is what is the standard error. So why we learn standard error? I'll give one theorem is there. I'll share that with you. And then we quickly get on to the thing. Bear with me if a time is going. As I said to you, this subject is a little difficult and I have to get onto the practical part also. But I thought this is important. If time is crossing, you have to apologize me on that. So there are two quick theorems, law of large numbers and weak law of large numbers. This is the best thing when we go out and talk to people, we should use this basis. The law of large numbers says that the sample average will be equal to the population average. So if I look at 100 as a sample, and we say that this is the same population average, people will question us, right? Let's take the politics. When people say that, okay, this time a particular party is going to win the battle because they have done a sample of 20,000 audience. How? Then the immediate argument, prior to the result is this sample is not correct. How can 20,000 people can define for a population of 2 crores? The reason is the sample approach averages to the population average if it is independently identified observations and identically distributed. So why it is important is we all have to see when we are doing for our valuation, for our business planning, especially, this is more for a business planning. Suppose if the management says that I want to come with a new product in FMCG, and this new product, I want to take it to the audience and I want to understand how my product will survive, or what is the people's expectations on the price or on the quality. There's so and so we can have various our own questions. Now we take a sample, right? We don't go and do all the people in and ask for it, right? To do that, the observations have to be independent. So if I ask a particular person X, the other person Y, their answers have to be independent. Both are not related. If I ask within a family, husband and a wife, then that particular sample may not be independently data points, because they could have an influence between each other. And that's very important in the case of a law of large numbers, says that if you are able to maintain that independence and the data distribution, whatever you picked up has the same data distribution quality. For example, it's a binary distribution. So whatever data that you collected observations, everyone should have the binary distribution quality. And if that is satisfied, then the sample average will always be equal to the large numbers. Now, you will ask me where it is useful for me. I'll go back to my example of valuing an inventory. In the valuing an inventory, or even if you want to value a receivable, you look at the data, what you're showing it, you identify that. Suppose if you identify out of 1 lakh pieces, go to one room where all are good pieces, very good pieces, there are no defects in that. That's a bad sample, right? You have, and that guy has influenced you and your independence is lost. He said, go to this room, collect these data points. That's incorrect. That has to be independent. And that's law of large numbers. But in practice, we find it very difficult. When we find it very difficult, that is when then we came with a story of weak law of large numbers, wherein he said that, okay, it doesn't satisfy this, but still the sample average will tend towards the population average, little slowly. It will run a little slow, but it will still go ahead with this. So now once we understand that why we are using, so tomorrow no one can question, if someone questions that, hey, listen, you have taken only this much sample, how do I get confidence from you? He said that, listen, this is how the law of large numbers talks about it. And that gives us confidence to give our answer. Okay. Don't get fear with the theorem. So I discussed this standard error, right? So now what I said in the standard error is nothing but a standard deviation. When I'm dividing by the square root of the sample, number of samples, that's my standard error. The lesser the number of sample size, the more is the standard error. That's what we said earlier in the formula. So here there's a central limit theorem. This is a theorem. Someone has done, mathematicians are too good. They said that if you have a 67% confidence, you can say that the population average will be equal to the sample average plus or minus the standard error. The standard error can be plus or minus because standard deviation can be plus or minus. Standard deviation there. No, standard deviation, when you get a value, you do a minus and a plus and you get a range. So then you can say with 67% confidence, your population average will be the same as this. And with a 95% confidence, you can do 2 times standard deviation. And now this is the central limit theorem, purely for the population average. So when again, especially for inventory and such calculations, we can use this standard error to determine the average error. Instead of just taking the sample, what we do today, mostly people take a sample and apply it directly on the sample and say this is the value. But probably they should not look at it. They should do an estimate. They should do the standard error and then say, determine the average on the low side and the high side of the overall population. Instead of just taking one sample average, I've taken out the range and now I know where it can actually fall. So at Chebyshev's inequalities, even further, it's even more stuff. They said that a minimum of 75% values will lie within 2 standard deviations. So he said that I really don't care it. I care a damn. I don't really bother. 75% will fall within 2 times standard deviation, irrespective of data distribution. It's a very classic thing. and it says 89% will fall within standard 3 standard deviation. So now using Chebyshev's inequality, we went into the new tandem altogether. So what he said is, if you have a sample growth rate of 20%, what it says is, I'm with a standard deviation of say 1%, for example, in your sample. So what you can confidently say is, listen, 3 standard deviations is 3%, right? So that means my data will fall 20 minus 3, 17, 20 plus 3, 23. So my data with confidence, I can say it is 88.89% between this range. That's irrespective whether it's a binomial, Poisson, normal, doesn't matter to me. That's what is Chebyshev's inequality. So it gives us to confidence when we talk about business decisions. It gives us confidence when someone, income tax people say that, hey, listen, why are we taking this number? You just give him this message saying that Chebyshev's inequality tells me that this falls here. So that's a good answer to probably the income tax. I don't know whether they will accept it or not, but you can actually use this. So this is a classic picture of Damodaran on a variety of distribution that you can do it. He starts saying that again, remember, start discrete or continuous. If it is a discrete, it follows a particular pattern. If it's a continuous, it follows a pattern. Then again, I said after discrete, whether it's asymmetric or symmetric, that's a second level of filter. So now you have a second level of filter, symmetric or asymmetric. Once we know whether it's symmetric or asymmetric, then we have various classifications of a binomial distribution, a uniform, discrete, geometric, negative binomial, hypergeometric, uniform again, a triangular, normal, and exponential, log normal, so on. I will try to give some of these definitions in the next 10 minutes, and then we'll go to the practical part of it. Monte Carlo technique, this is theory. It's a computerized mathematical technique that allows people to quantitatively plan for risk and decision making. As I said to you, what's my probability that I'll not make loss? Okay, 10%, 15%. You are giving a percentage range. It's a probabilistic interpretation. How do we do it? We generate a random. Remember all this, we kept on using the random variable, and I was harping on it. What Monte Carlo does is, we cannot go to 10,000 people and ask, right? So what it does is, in computer, it is generating as if you have asked someone a random variable. And that's all it's doing it, using a random variable and then saying that random variable follows a distribution. And based on the distribution, the random variable generates. Because today, if I sit in front of a computer and I don't give a distribution and I just give a random variable, what it does is it gives me a random variable, but that random variable has no distribution pattern. But the moment in Microsoft Excel, when they say, okay, I generate a random variable using this distribution of binomial. So whatever random variables I get generated, that random variable set, if I were to plot a graph, it will plot me a binomial distribution. If I were to tell the computer in Microsoft Excel, okay, generate to me a normal distribution using random variables. So the random variables that Excel will generate will actually, when I plot a graph, it will have a normal distribution. So that's exactly, so we are telling Excel, generate random variable, but I will tell you which distribution, you just do that for me. We are directing computer, and that's what it is. So when you have multiple inputs, so here I have a sales growth, which is uncertain for me. I have a gross margin, which is uncertain for me. I have an interest cost, which is uncertain for me. I have a reinvestment. How much of capital investment I have to do it? It can vary. That's uncertainty. Working capital, uncertainty, how much I require. So each of these is for me an input. For all these are input for what? Say, for example, I wanted to calculate the fair value of the company. So one fair value, I have multiple uncertainties on the input side. Each input, I'll create a distribution. For each of these, collectively, I get an output. That output is my NPV. So I have multiple inputs for getting that particular output NPV. And that's my value. And that's a distribution. Then I make a decision. Kindly note, garbage in, garbage out. So why we did a little bit of reading here, if we don't pick up a correct distribution, then it goes wrong. Now, don't get complicated. In finance, it's relatively easy. We follow standard 2-3 distributions, but it's important for us to know that we are using it right. Otherwise, we can be questioned. Only thing, the person who is questioning should also know a little bit to question. Otherwise, we can easily escape. So we determine the variables that represent the source of uncertainty. Okay, sales growth. Okay, that's a variable for me. Gross margin, yes, it is variable. Interest cost, no, it's not. So I'll not consider that. Working capital, probably yes, because mine is a working capital intensive. So I'll consider that. CapEx, not probably, because I'm in a trading business. It's not uncertain. So I'll not consider it. So like that, you identify the variables. If you identify too many variables, it's difficult. For the sake of our problem today, I have identified almost many, just to give perspective. But otherwise, you can pick up a limited number here, which you feel has an impact to make a decision making. Identify a distribution. Okay, sales growth follows this distribution, gross margin follows a particular distribution, and interest, working capital, something else. And then I know that I have the distributions, I start iterations. Now, iterations is, I remember last time, I think Mr. Rajesh has given me a number. What is the number you have to do it? In Excel, yes, I have done 10,000 iterations. It's difficult. Excel will be a little slow, but yes, you can do up to 10,000. If you have softwares, you can do much higher. And then using that, you can make a confidence decision making. So quickly, under the standardized discrete data distribution, finite values, we have Bernoulli trial. Not much of it, we don't use it. Binomial, we know, we heard about it. Poisson, so hypergeometric and geometric. Geometric, I think it's also called a negative binomial. We will not be doing much because for finance people, it's largely a continuous distributions. Okay. So we will be going through that, Mr. Tarun, for sure, which distribution in a practical, I'll show. These discrete data distributions are very much useful. My Excel file does have some small examples, less of Monte Carlo in that, more of business decision making. So I'll give an example to you. When there are walk-ins to a restaurant, and I say that historically my restaurant, I have every hour 30 people come into my restaurant. That's a data point that I have it. So during lunchtime, a particular person coming in a particular time has no relevance to the next person coming. That is completely independently distributed. So there is no impact on it. Then I can say, okay, what is the confidence over the next 5 minutes? How many will walk in? What is the confidence that how many will walk in over the next 20 minutes? Because I have a data point set, in an hour, I have 30 people. So Poisson distribution helps me to tell me over the next 5 minutes, next 15 minutes, how many are likely to come in. Why it is useful? One is, when you were to plan, we have this working in shifts, right? So when you have people working in shifts, we don't get many calls in the later part of the night, evening. When we don't, in a BPO, we don't have anyone in the mornings, we have in the peak time. This actually Poisson distribution helps us to actually plan like that, how many we want to do it. That's a business decision. Like that, we have many other decisions which we can actually take. For example, a marketing decision. So marketing decision is, this is again a classic given in the public domain. I'm conducting a BVA event. The cost of a BVA event is say $1 lakh. BVA has conducted this event, fantastic. But BVA has a hidden agenda. BVA's hidden agenda is they get more people enrolled with BVA, and there's an enrollment fee, and that fee is their income. Now, BVA says that historically, the experience is that when they have conducted a BVA event, they have made a 10% probability. So if there are 100 people who have participated in BVA event, then 10 people have converted. That's their statistical probability. I can actually use a binomial distribution to actually estimate whether I'm going to make a profit or loss. That I'm not estimating profit or loss. I'm going to give a probability that with this confidence, you're going to make this is the probability. What is the probability of you making loss? Probability of you making, these are the business decisions. So most of this binomial, Poisson, geometric, these are business decisions. There are examples. I don't think we will have time for those Excel. That Excel is there. I share with you what I understood it. And if there are any others, please come back to me. But today we'll be focusing on the Monte Carlo because this discrete distribution, not much of Monte Carlo is applicable here. So I'll quickly go to the definitions. A binomial distribution measures the probability of number of successes or failures outcome in experiment each time. Successes or failure, visualize always it's a binary. Either employee leaves or employee stays. It's a binary decision for attrition. or either a person enrolls or he doesn't enroll in a marketing event. It's a binary decision. So it's a very binary decision. There's only two outcomes. In binomial, there are fixed trials. So I say there are 100 people participated. That's a fixed, 100 is a fixed number of trials. Only two outcomes are possible. Either he will stay or not stay. Either he will convert or not convert. And the probability I should know about it. And one decision, one trial should not be affecting the other. That's a requirement. If that is not satisfying, you cannot use a binomial distribution. I have given examples in my Excel file. You will like it because we are for Monte Carlo purpose. Directly, we don't use it. So I have not done it much. For binomial, I have done Monte Carlo also, but that's why I'm not going through that Excel. It will be there. Poisson distribution. Poisson distribution is, as I said to you, walk into the customer. I have only a probability. I only have one number. Over a period of 1 hour, I get 30 customers walk into my restaurant. That's all data I have it. But each person who's coming into the restaurant are not impacted. In real world, it gets impacted, right? When you go to a restaurant and you see it's already full, you walk away, right? That impacts. So, but we need to know that this distribution means we should not be getting affected. We should know about that. Once we know the probability, then we can actually probably say that what is the probability that I would have this many customers walking in the next so much time, so that I can plan my manpower accordingly. It's a very useful distribution from that perspective. The only parameter here is you need to know the probability. In a binomial distribution, the parameter that you need to know is the number of trials, 100 people coming in an event, and the probability of customer getting converted. And remember, the total probability is always 1, right? So if number of people getting converted is P, which is success, in mathematics, you use the notation Q for failure. So 1 minus P is failure, Q. So in a binomial distribution, when you know the success is P, the failure is 1 minus P. You know both the probabilities for a fixed trial. In a Poisson distribution, there are no trials. You just need to know the probability, and that's good enough. Hypergeometric distribution is a discrete distribution that measures the probability of a specified successes without replacement. Now, very interestingly here, the key word is without replacement. So again, you take a example that I have a basket of employees, say 100 employees are there. Out of these 100 employees, you are picking up a sample. Out of these 100 employees, there are, say, 70% male and 30% female. That's a clear classification, right? So you are saying that you are forming a committee and you need to pick up 10 people. So the moment you are saying 10 people, you don't know whether all 10 will be girls, women, or men, mix of men and women. And in such scenario, because you are not replacing, you are not picking up one person to the committee and putting back that person in the population of 100. You are taking it one, the remaining are only 99. You're taking the second person, the remaining are 98, so on and so forth, right? So that is where, whenever you have a case, and then an example I've given in the Excel, how to use a geometric distribution, hypergeometric. I tried to put some numbers there, but the messaging is whenever there is no replacement, whenever you're pulling up things and it is not going back to the population, you're supposed to use hypergeometric. The key word is without replacement. So this example, and whenever you are worried about distribution, when to do, go for the simplest example to get your concept clarity and go back to that again, and go back to the problem again. That would help you. And last one that we're going to discuss on discrete distribution is geometric distribution. It's a discrete distribution that measures the likelihood when the first success will occur. What it means for success is, suppose a market research person, when they're going and they say that, listen, go and convert customers. The probability is that he meets 10 people before the first success happens. That's an average, right? The 10th is a success. First 9 will fail. Now, that's the pattern that we have. So it gives me a distribution to measure the first success will occur. All the before that attempts are actually a fail. So you are doing your trials, you do out of 10 trials, first 9 trials fail, then the success happens. Why it is useful? When it is useful, it is probably an example is when you are trying to do the business plan. As I said, this is a strategic decision. It is less of valuation, it's more a business strategy. So you have made a projections for the next 5 years. Hey, listen, I'm going to make this projections. Everyone is gung-ho, right? Year 1, year 2, year 3, year 4, year 5. Now what happens is the sales are dependent upon is essentially your employees are able to sell the product. And when the employees are able to sell the product, then you need to know when they are going to sell, what is the likelihood of they able to sell the product. Then you have to make an estimate. What has been a pattern? My pattern says that I have failed so many times. Now, if every 10th person I'm converting, then how many people I'm not put up here, but just visualize this. How much time it takes for me to meet 10 people? Me means for an employee. Okay, it takes say one day. That means in a day, the conversion can only happen one then. Now, if conversion can only happen one, in a month, there are say 25 working days. So I have only 25 conversions in a month per employee. And if I have 25 conversions per converted customer, I get this much revenue. And therefore, this is my revenue. If I want to do the unit economics, I take this revenue, I subtract the cost of the employee. That's my contribution level money, profit that I made from that employee, which is typically most of the IT companies do, right? Each employee, how much of revenue, how much is the cost, what's the profitability. And that's where we are supposed to do. So these distributions help me. And then go back to the distribution revenue and projections, say, hey, listen, you said this is the growth projections, you will have it. But this is the probability of your employees generating business. That means you need so many employees. Show me how much of employees you have here. Then the answer would be, no, I'll have improvement in the productivity. And then therefore you say that, okay, that's an assumption you're making, that your employees are going to be more productive. As if employees are productive, you will achieve these numbers. If employees, so while the sales growth itself is an uncertainty, employee productivity is an assumption, it's also an uncertainty. If that varies, the confidence will vary. So we go back and start discussing that. So that is how we'll use it. This discrete distributions less for Monte Carlo. It's more for business planning. The topic was also for business planning. So I brought that. In Monte Carlo, someone asked me, tell me which techniques. Largely, we can follow 3 techniques: normal, triangular, uniform. Triangular, most frequently used. There's a limitation for triangular also, I'll share with you, but that's the most convenient to use it. Normal distribution, you should know what's a normal distribution. Once you understand, it's fine. And there's also a uniform distribution. We'll be using all this is in our Excel file. I will be going to the Excel file. I have another 30-40 minutes. We will go through as committed as part of our expectations. First is uniform distribution. Uniform distribution is the most simplest way of saying that. Okay, before that, let me explain to you that with the continuous distribution, 1 point. In a continuous distribution, the probability of any specific value is 0. So let me explain what does it mean. Again, in a discrete data distributions, so I say that my interest rates is 18%, 19%, 20, 21, 22, 5 possibilities are there. The probability of interest rate being 20% is say 40%. Probability of 18% being say 5%. So I'm giving a specific number. I'm able to give a probability for that particular rate. 18% probability is 5%. When I say interest rate is a continuous distribution between an 18 to a 24%, if that's the range I'm saying, it's a continuous distribution. It can be 18.1, 18.2, 18.23, 18.45, 19.3. It can be any number, but the probability of that any number, which is probability of interest rate being 18.2345 is 0, almost 0. That's why it's called continuous data distribution. So I repeat once again, just I don't know whether everyone understood it. In a discrete data distribution, you are able to assign a probability for a specific value. In the example I've given, 18 to 24%, if my interest rate ranges, where I said 18%, the rate is probability is 5%, 20%, the probability is 40%, I have a value for 20% probability is 0.4, 40%. In a continuous data distribution, it can vary, the range could be anywhere from 18 to 24. It could be anything. It is so difficult, it is so uncountable that the probability of that individual value 18.2345 is almost 0%. That's continuous data distribution.
But Ganesh, Sanjay here,
yes, sir.
if we add all of those small bits, correct? 0 yes. Tending towards 0, correct? Then it will make it 1, correct?
Yes.
Then all of it is aggregate to 1.
Yes.
So right. I mean, we are saying that a value is distributed so large that for a particular point we can't estimate. It's almost equal to 0, but all of them will aggregate to 100, yeah, or 1.
Absolutely. Absolutely.
Yeah.
The probability is between 0 and 1. Yes, absolutely.
Okay.
So the uniform distribution. So uniform distribution is I have a minimum and the maximum, A and a B. So I said that 18 and 24% is my interest rates. My mean is the average, A plus B by 2, 24 plus 18 divided by 2, which is what we use mostly in our lives. And 21% is my mean. That's it. So change of any number is equal. It is. So at any point of time I see it. So for example, at 18.1, if I want to see, it is nothing divided by 1 divided by 24 minus 18, because 24 is higher, 18 is the lower. I have this. So the probability of 18.1 is equal to the probability of 18.2, equal to the probability of 18.2, equal to the probability of 23.4. So all this, so whatever is the probability at any point, they're all equal. All the data points have equal probability. That's uniform distribution. It can be both discrete and continuous. So uniformity is where I gave an example earlier for the same interest rate or growth rate, whatever you call it, 18 to 24. I said probability of 18 is 19.95. Probability of 19 is 20.05. Probability of 20 is 19.98 percentage. Probability of 24 is, say again, 20.24. So all are in that range of that 19.9895 to 20. So they're almost same, right? But I have given a specific discrete number, 18% interest rate, 19% interest rate, 20% interest rate. So, but they are uniform in nature. That's called a uniform discrete data distribution. Same example, if I say it's a continuous distribution, but probability is the same, 18.1 has the same probability of 18.1% interest rate is same as probability of 18.2% interest rate, as same as probability of 23.1% interest rate, then that's continuous data distribution. But both are uniform in nature. And what do we do here? How do we generate data points here? We take the minimum, which is 18%. We generate a random number and then multiply it with the max and the minimum. And that is how you can generate various data, uniform data distribution. We'll see it in Excel file. Normal distribution. The normal distribution is actually, most of us know about it. I don't think much in Spanish. It's a bell-shaped curve. So we know it's a bell-shaped curve. It has a central mean is there. And the values can go to minus infinity to plus infinity. The reason in finance is, for example, if you were to take a stock price, it doesn't go to negative, right? How do I apply a normal distribution for a stock price? It has an end value 0, but the right side value can go to infinity. So it's difficult, but however, for ease, people do use it when the negative numbers are very small. If the negative numbers could be larger, you should not use it. If the negative numbers are so minuscule, then you can use a normal distribution. Basically, mean, median, mode converge in a normal distribution. Let me go to the last one, the triangular distribution. It's a continuous distribution, which is actually inadvertently we use in our lives, which is the minimum. We say, okay, what's the most likely that you will not go below this particular growth rate? So that's, I will definitely grow 10%. 10%, I will not grow below 10%. So what we are essentially saying is there's no value below 10%. Everything has to be 10% and above. That's minimum. The maximum on the other side is other way. But the maximum, I cannot grow more than 30%. It's not possible. My capacity does not support me. My manufacturing capacity cannot support me. My manpower planning does not support me because it has to support, right? And that's why I have a maximum of 30%. I have cut off 30%. Okay, great, 10, 30. Okay, what's the most likely? What's your gut feel? Where will you fall most likely? That's where you say, okay, one, if it's symmetrical, I will say 20, 10 and 30 average is 20. I'll say 20 is then that's a symmetrical distribution. If I say, most likely is 15%, then it's asymmetric, but yes, still, but 10 is the minimum, 15 is the maximum, 30 is the maximum, and 15 is the most likely. That's where it is. Now, there is also a distribution called a PERT distribution, which I'm not capturing, because PERT distribution and all, they try to smoothen this curve if it is asymmetric. Ideally, they should be used it. But Excel does not have that distribution available in, they have PERT dist is there, but a certain complexities. Triangular is easy, but a modified form of triangular would be PERT distribution when it is asymmetric. I'm using triangular in this, but essentially when I skew the most likely towards the symmetrical point, essentially it becomes symmetrical, right? So triangular is essentially symmetric. It assumes reasonably symmetrical. Therefore, the mean is a plus b plus c by 3. In practice, it will not be the case for us, but that's an approximation that we will do. Trust the theoretical part, probably a little boring part. You have heard and understood it. So any questions before I get into the Excel file?
Just one thing, let me know when to run the poll questions because this is a CPA credit hour program.
Okay, the choice is yours, Shilpa. Either whenever you take a call, I'll just be silent about it, or you can run a CPA. And only thing is, I'm afraid 9:30 is the cutoff. I'll try. We'll understand. Why don't you run the CPA right now? I'll also take a couple of minutes break by the CPA. Is that okay then?
Yeah. Shall I run the first poll question now?
Yes, you can run all the questions actually.
Oh, thank you. Just give me a minute. Can the participants see this poll question now?
Yes, Shilpa.
Yeah, Mr. Ganesh, you would like to.
Ajay, explain to me. These are very simpler ones, I think.
Yeah, which is the right one you can.
Ajay, I have to get the answer also. Okay.
Yeah.
And the first is binomial distribution. It is depends on which of the following: sample size and probability of success. B.
Okay.
It is the mean is n and p. So the number of trials is required and the probability of success is required.
I request the participants, especially who have paid for the CEP certificates, to participate on the poll questions, which will be submitted to IBBI.
Okay, Shilpa, should I answer?
Yeah.
It's a mean and standard deviation. For normal distribution, it's always about a mean and standard deviation.
Why is the question not showing?
It is actually reflecting. Maybe some of your settings. I'm getting the.
No, I could see I could see the first two questions, but this question, I can see only the screen.
And the answer is C. 95% is within 2 standard deviations. Normal distribution is a very interesting thing. 67% is within 1 standard deviation of the mean. Data will fall within 2 standard deviations with 95%, and 99% is within 3 standard deviations. Yes, Shilpa. Yeah, it is continuous random variable. It can take any value, right? We just discussed uniform distribution, right? Between 2 variables A and B, if it can take any value, it's a continuous random variable. How many more, Shilpa?
I think this is the 5th one. Am I right?
Yeah. Is the last one?
Yeah.
Yeah. The answer is 3. It's a uniform distribution. So the average will come out.
Looks like few people were confused. Is it that easy or we are not getting it? That's why we have something.
That's okay. I think all of us are learning continuously. So it'll
Just
come
one
out.
last.
One more is there? Okay. I'm more curious to get out of this. This is an unfair question. Okay. People who knows, they will respond.
In exams, we get out of syllabus questions like that.
No. Actually, in my PPT, I have named it, but I think I never later deleted the line. It's done. Okay. The answer is, first of all, definitely, if someone would have given between none of this and Gaussian distribution, I would have been okay. Because Poisson and Bernoulli are discrete data distributions. Normal distribution is a continuous data distribution. So those two are ruled out any which ways. As compared to Gaussian, yes, it's a Gaussian distribution. That is, it doesn't tell you any knowledge except that you are respecting the learned person. It's a Gaussian distribution. Okay.
Yeah.
Shilpa, I have to give prize for people who get all right.
The people who have done stats are not allowed to Subhadra.
Excluded category.
So shall we start, Shilpa?
Yeah, Mr. Ganesh, over to you.
Yeah, sorry. So now, I don't know, it's not coming in. Share. Okay, here, my Excel will be sometimes a little slow because there are some simulations done. The file is a little bigger to that extent, but we'll understand and carefully we'll go through certain numbers. So this is my income statement and the balance sheet, hypothetical one. We are saying that the balance sheet has 80 lakh, fixed assets 60 lakh, and current assets 20 lakh. Current assets has inventory, working receivables. On the equity side, we have reserves and surplus, equity capital, and then the long-term borrowing, short-term borrowings, and of course there are trade payables. And therefore, the net working capital is 5 lakh. On the left side, we have income statement. The company has earned 2 crores worth of revenue. I don't have the split based on the price and the volume. The margin is 20%, therefore gross profit, it is 40. And these are completely numbers just created randomly. Okay. SG&A, it's a 2.5% of sales, which is 5 lakh. And therefore, I have my EBITDA. And of course, then I have a depreciation, some number 16. And therefore, the EBIT is 19 lakh. Interest, I have calculated again, saying that interest is at 12%. So what I did is interest is at 12%, and I multiplied worth 20 lakh because my long-term borrowing and short-term borrowing is 20 lakh. So 12% of 20 lakh is 2.4 lakh. That's my interest. And therefore, I have PAT. So I have calculated the DuPont equation because I'm very fond of DuPont equation. Return on equity. That's a different lecture altogether on DuPont. It's quite complex and very interesting. And therefore, the interest rate, this was the assumption, and the debt to equity and debt to assets. So this is the day one, day zero, whatever I call it, reinvestment ratio. So one of the principles that we need to look at it is, especially when you're doing a terminal value, is what is my delta capex upon delta sales. So one is here I want to bring into the notice, there's a book depreciation, there is a business depreciation, or what do you call actual usage of depreciation. I'll give an example just to give my perspective here. Assuming you have a printer shop wherein you actually print papers to various customers. Now the printing machine has a capacity of say 10,000 pages. So when you're growing at a particular sales, you depreciate the machinery, saying that you depreciate it over 5 years or 3 years. That's a standard depreciation, right? You do that's a book depreciation. Now, imagine your sales have grown so significantly that you have printed 9,000 pages in a year. Now, the book depreciation, say, if I do in 3 years, 30%, but my business depreciation, if I were to say, I've done 90%, right? Because 9,000 pages are done, the machinery will be dead after another 1,000 pages. I need to reinvest. Ideally, the auditors are supposed to look at the actual usage. The management is supposed to give an actual usage and then do the depreciation. Mostly it doesn't happen. We all know that, right? So from a valuation perspective, I always say that if possible, to the best of the ability, wherever it is applicable, if the growth rates are going significantly higher than the past, you may want to understand the capacities, the assets, which are depreciable assets, to relook at it and identify the depreciation. So one of the ways to look at it, the reinvestment ratio. So what I did is, I said, whatever is the sales is there, delta sales, I'll do the reinvestment in the delta capex. So that always my company has a similar amount of capacity for maturity. And this can vary. For math, for my example purpose, I've taken this as an 8%, saying that this is what I'll reinvest every year so that my capacity is not getting curtailed for my growth rates. My working capital is similar. I have taken sales, and my sales for delta sales, I'll have a delta working capital requirement. And that's where I have to fund. So whatever is the delta capex is required, a delta working capital is required, I know how much of proportionate debt I can get it, because my debt upon assets, I have the ratio. So I know the corresponding proportionate debt that I will be requiring, and therefore I know the interest that I'll be paying for my projections. That's one way to look at it. And therefore I have the cash flows. So that's my free cash flow. So here, what is the business decision we are looking in the Monte Carlo? We are saying that we want to do the confidence level of a particular NPV that we are going to achieve. That's the business decision we are going to take today. With what confidence we are going to tell the numbers. Now, there are so many uncertainties in this. Before that, let me quickly get in. Cost of equity, I put a number, and I know the debt to equity is changing. Therefore, I've calculated the WACC. And terminal value, I have taken sales multiple. We all know we can take sales multiple, which gives me an implied growth rate, or we can take a growth rate also. One of these can be used. Based on the above, I tried to understand how did I get my sales. So I realized that my sales volume is 2 lakh and my sale price was 100. Therefore, I got 2 crore sales. Okay. So if I were to look at it, my sales price has a different data distribution as compared to the sales volume. Because price, I might be sensitive to the market. Sales volume is a function of my capacity, completely different. One is a market determinant, one is a capacity determinant. So what I said is, let me split that in my Monte Carlo technique. And I prefer typically when we are doing modeling to look at always the capacity, then directly to the sales growth rate. Gross margin is 20%. Okay, we have a number there. And this is your SG&A. This is 8%. So the number has to change. I think that formula did not get saved here. So let me just change it here. 8% times, and I don't think it, I just do like this. I don't know. It takes some time. Okay, that got changed. Okay. Now here, EBITDA percentage to sales, therefore is 12%. Sales to operating capital assets. This is a ratio for the DuPont equation. What you have it, that's the number. Essentially what you're saying is net margin we have it, we have turnover we have it, debt to equity, the financial leverage, we have taken that number. Working capital to sales ratio we have taken, and this is the various numbers. These are static numbers, today's numbers, right? So now, what are the distributions that I have considered here? I said sales volume, when we discussed with the management, they have given me 3 numbers. This is my minimum, this is my maximum, this is my most likely. We can actually use triangular for all also, but for the simple, depending on the data point that we have here, for the example here, I have taken for sales volume, I have taken triangular because management has given me 3 estimates. And it's a continuous, it can vary. It's a quantity, right? So I said it can vary from this number to this number anywhere. So let me use that. Then I have the sale price. This is a discrete, non-uniform. Because here, it is, while inflation is there, market may not accept the higher price. Therefore, I have got specific probability that it will be a particular at 100 rupees, a particular price, 101 rupees, it will be a particular price. I said, let it be a discrete, non-uniform. Gross margin to sales, I said it's a simple normal distribution, easiest to use it, and reasonable good estimate to consider that. Gross margin would vary with a mean of a particular 20%, with a standard deviation of 1%. It can vary, it's a percentage, so I'll consider it's a normal distribution. SGA percentage to sales. Here, it's a uniform continuous distribution. So tomorrow, in one of you might question that, are these exact ones to be used all the time? No. This is, for example, I've done it. You can pick up based on the data points that you have it, but more or less we can follow some of this. You will not be wrong. Suppose sometimes you feel that you are seriously getting wrong, use different distributions to figure out how much the data is varying for you to get confidence level, whether you're taking it right or not. So uniform discrete is what I have considered. And therefore, again, I repeated couple of others, just to see where it was. So this many variables are not required when you're actually doing in real time. But yes, whatever has a serious significance of uncertainty. One other thing I wanted to do is terminal value uncertainty also, but I didn't do it here because it was going long. Later on, I realized I didn't do it. You can do that as well, because if terminal value growth rate is going to be a significant parameter, you can use that as well. Contingent liability is a forceful fit in there. What I said is there's a liability of value so much, there's a 50% chance that I'll win the case or I'll lose the case. I said, let me try that and put it here and see what would happen to my NPV. How do I do this?
I had a question.
Yes, sir.
Hello?
Yes, sir, please. Please.
Go ahead, Mr. Telang.
Yeah. So gross margin percentage to sales, normal. Now, gross margin is basically your sales price minus the cost of your sales. The cost of sales itself could be discrete, non-uniform, or whatever else. I'm not sure about that. So how would you say gross margin percentage to sales normal?
As I said to you, the distribution that I have considered here for explaining how to use the distributions.
Okay, got it. You can refine, keep on refining.
Yeah. So the messaging is, I wanted to put all the distributions under various sets to show how it is falling, to figure out how to use it, and then actually say it. Okay. And these are basically to give various distributions how to go ahead and use it. And as you rightly said, I don't need to do all the 7 also. I can actually pick up anything which is on percentages terms. So since you have asked that question, just for a hypothetical case, if I'm in a completely service business, which is completely on manpower, okay, how can my cost be discrete? So the problem is, if it's a manufacturing sector, if it's a trading sector, if it's a services sector, each one has it. So there is no one uniform pattern. Some people actually use only normal throughout. Some people use only triangular throughout. So it's not about what to do it. We should, if you're able to figure out what is most appropriate, and wherever we are doubt, we use 2 different distributions, estimate it, and see where we are falling.
So that's in this sale price, you have said discrete, correct? Sale price can take any value. So it should be continuous rather than discrete, correct?
No. See, the reason I said is, I'll give if you see the number here, sale price I said currently is at 100. Yeah. I said in year 1, it can go to 101, 102, 103, 104. This is what the management has said.
So then it is discrete. Oh, got it.
So then I said, the probabilities are varying, right? Someone said 15% is 100, 30% is 101 in year 1, and year 2 is 50. So for some, I did not change for all the years. I just put the same numbers. For some, I did change it. This is purely just to give a perspective. You don't need to change for year on year, because if a company is growing, there's no reason why year 1 numbers will be the same as year 2 and year 3, right? So therefore, I said 5 years, if you can plot it, you can actually do the budgeting for 5 years. Complete business planning can go for 5 years like this.
Okay.
Now, if you see the sales volume, so I've given the minimum, the maximum is 20. So all the data points will fall between a minimum of 10 and a maximum of 20, and most likely it will be 15. So now here, inadvertently, I said it's a symmetrical distribution. It can actually be most likely be 12%. It can fall in asymmetrical distribution there. Sale price, I have said it is various probabilities. The probabilities are not same. Not everyone is 20, 20, 20, 20, 20. So it's not uniform. It's a discrete, non-uniform distribution, because the probabilities are varying for different pricing. Gross margin, I said the mean is 20%. It can go just 2% down or 2% up. That's what typically mostly we say, the deviation, historical data we see, and therefore we say standard deviation is 2%. So essentially what it means is, at a 1 standard deviation, I might be at a 18% and a 22%. If I'm at a 2 standard deviations, I will be at a 16% and 24%. And if I'm at a 3 standard deviations, which is at 99% confidence, I'm at a 14% to a 26% range. That's the range. And that is how I'm going to plot the data. Then we have selling general administrative expenses. This I said uniform distribution between the low value of 8% and high value of 10%. So I'm saying that it can fall anywhere in between. There's a uniform probability. I just said 8%, 10%. Now we have covered triangular, we have covered discrete non-uniform, we have covered normal, we have covered uniform distribution. And again, I repeat again, you don't need to use so many distributions in your practical cases. You can actually pick up one or two, or probably only triangular with the data points from the management. And of course, the historical data should support that. Delta reinvestment to delta sales. Here, I have said uniform distribution, but discrete, because I said I have probabilities which is almost uniform. Everything is around 20%. So this is uniform in nature. So why can't I consider it as uniform discrete? So we said we can also have a discrete uniform distribution. This is one example of that. Again, working capital to sales ratio. This I said it can fall as a uniform distribution between 5 and 6%. It can fall anywhere. So that's the number. Interest rate, I called it a triangular distribution, but asymmetric here. If you see here, minimum is 11, most likely is 12, the maximum is 15. And then contingent liability, I said there's a 50% chance I will have a liability, 50% I will not have a liability. Only thing is in year on year, what I said is the cost of interest, if it gets delayed by a year, it's a hypothetical number. I said it's 12%. And I just presume that the liability will increase if the liability were to happen in the later years than in the first or second year, like that. So now here, these are the number of, so we tried to cover these 4 or 5 distributions and how do we actually apply for our Monte Carlo technique. It's 9:20 Shilpa. Do I have a privilege or luxury to cross 9:30?
Yeah, I'm sure audience will be happy to listen to you more.
My apologies if I'm not able to cover up for some people. Very
Because
sorry
this is
about
the climax of the movie.
Okay. So now let's start. So here, there's something called as a C variable. This is just a notation C variable. What you are saying is for easy calculation, or for whenever to do it, this is nothing but the max. If you see D74 minus 72, what we are saying is 74 is most likely, the lower range. 74 is most likely, right? Minimum is 10%. So what I'm doing is I'm doing the ratio of most likely minus minimum divided by max minus minimum. So if I'm not able to draw it here, visualize a triangle. I don't know whether I can, when I do a word, how do a triangle in a quickly? I don't know that. I don't know. I can do it. Not that fast. So
you can use whiteboard.
Whiteboard. Okay. Let me try that. Whether so people can use it. How do
Or
I
annotate facility also can be used.
I'm not able to see my own screen. Why is that? I don't know. Excel file, I'm not able to see this. Okay. See this Excel, so whiteboard, where do I know? So we just visualize a triangle and draw a line in between. Okay, visualize a triangle ABC. Okay, draw a triangle. So triangle got divided into 2 triangles, right? It need not be, when you divide it, got into divided into 2 triangles. Now what happens is when you draw, it is 2 right angle triangles. You have one is a lower triangle, one is a higher triangle, because the most likely is falling somewhere. If the most likely is a symmetrical distribution, it will be exactly in the middle, and it will have 2 equal triangles. And if it is in the most likely it's an asymmetric distribution, when you draw a line from the most likely down, because you have the base is minimum and the maximum line, and the topmost point is the most likely, you draw, and that is where you get 2 triangles. So this ratio is most likely minus minimum, that is on top of the lower range, and the maximum minus the minimum, that's the maximum range, that's the ratio. Why am I using this ratio? I'll tell you now. This ratio will be between 0 and 1, right? Now, I am generating a random variable. I just use a rand function, which all of us can use in Excel. It generates a random variable between 0 and 1. I am saying that is the probability. That's a cumulative probability. I'm saying that corresponding to this probability, where is my data lying? So here, if you see in this example, I see 63.9% is my probability. That means in a triangle, when I divide it, it is falling on the second part of the triangle. In the two triangles, when the lower range and the upper range, because I have taken a symmetrical distribution, it is 50%. So the 63.9% is more than 50%. So it is falling on the upper range of the triangle. Based on that, the estimate that I get, this is the formula, which is it's available. I'll share it with you. It's a simple mathematical formula. It is telling me that the value probability of this particular random simulation is 15.76% growth rate. Because 15 was my most likely, right? The probability of random number generation gave me 63.9%. In other words, it is more than 50%. Therefore, the estimate that I got is 15.76%. If you take the year 2, my random number generation gave me 42%. That is in the lower range of triangle. That means my estimate of my sales growth rate will be below 15%. That way it's 14.61%. Again, in the third year, it gave me 56%. That number of 56%, 42%, 63.97%, it's a random number. I'm not generating it. It's a simulation. I did it. I said, system, you just throw me a number. And once it threw me a number, I actually calculated where my probability estimate of my growth rate will be using a triangular distribution. So when you see, when I have a probability of 23%, the estimate is 13.4% because I have a minimum of 10%, maximum of 20, most likely that 15%. That is why you see this particular estimate getting generated because of the random number. I didn't do anything. Suppose if I press F9, and it will take some time probably, these numbers will change because random number is going to change. It's going to give me a different number, and therefore I'll have a different estimate. This is how I am going to plot for my triangular distributions. When I have a minimum, when I have a most likely, when I have a maximum, I am going to populate. Now, what am I doing in Monte Carlo? What I'm doing is I'm going to generate 10,000 times random numbers. When I'm going to generate 10,000 times random numbers, each random number is random in as a character is going to give me a different probability. But the probability will follow a triangular distribution. Therefore, when I'm using corresponding, what is my growth rate against the random number has nothing to do with our life. It is just giving me a number between 0 and 1. I just did a F9. I don't know whether all of you can see the change in numbers in the estimate. Can you? Or only I can see it?
Yes, sir. Change is there.
Yeah,
So,
there is a change.
Change is there.
99%. From 66, it has been 99%. And
Right. Earlier it was 63%.
yeah.
So
And
what
from-
it did is I am following a time. So when I plot this 10,000 times random number, I get 10,000 times an estimate. Which all the estimates, if I were to plot a graph, it will be a triangular distribution. And then therefore, what you're saying is, I am saying that management has given me these numbers, and therefore these are the various growth rates that I can come in. I am not taking a point estimate of 10, 15, 20. I'm actually plotting to determine for myself what is the likely outcome of each of this. This is for sales volume. So triangular distribution, from a simplistic, easy, use this formula, generate a random variable, determine a C variable, you get the value. I mean, if one were to not understand, that's it. But that's the outcome of triangular distribution.
Now, I had a doubt.
Yes, sir.
So in the triangular distribution, the most likely, there would be a percentage, right?
Yes.
When we say most likely, it doesn't mean all. I mean, all these parts of the triangle are not equal. Most likely would be, say, above 50%, 60%, whatever.
It depends on the distribution, sir. That's exactly what you're saying. When you say most likely, you are telling already it is 50%, 60%, depending on the data point that you give it. Suppose if you were to give a 10, 15, 20, it's a symmetrical distribution, then most likely majority of the probability will be at 50%.
Yeah, okay. So in that itself, I'm just asking a question. So by giving a certain value of 50% probability, that itself will influence the overall result, meaning in terms of what the sales number will be. What would the random numbers which are generated, how much they would influence the overall result versus the fact that you have given more than 50% to a certain value?
Okay. What is the probability given this ratio of 10, 15, 20 percentages of sales growth rate, which is a triangular distribution, you are 75% confidence level that this growth will be so much. You have given me a point estimate of 50%. I understand. I'm asking for 75% confidence level. What is the probability that I would not have below this quantity of production sales because I'll have a serious production problem? The production problem will happen because I cannot stop production. Some of the factories cannot be stopped. It takes shutdown, will take time and all that. They need these estimates, right? They need to know where will they stand. So it's not always about the mean every time. So what we are saying is, when we are giving a range, when we are giving a probability, we are giving a business decision. What is it that I'm foregoing? What is it that I'm taking risk for? Is essentially what is being telling for data distribution. Yes, when you say mean is skewed if it is asymmetrical. In this case, 10, 15, 20, it is symmetrical. Mean is always converging, right? But we do, because the average, if it is tending towards this, the average is tending towards the mean. If it is asymmetrical, 10, 11, and 20% growth rate, then how do you say where will it fall? How will you determine your probability? Will you take a most likely of 11? How much of data will fall at 20? What will happen? What confidence? This
so that actually that's the point, that if it is symmetrical, yes, but let's say the management is biased for a particular number. They put a very high value as the most likely. My question is, irrespective of the Monte Carlo method, it will be biased towards that particular value, the higher, more optimistic value. Is that the correct statement?
Absolutely no. Can I deny that? Absolutely no. Because we started saying that sampling band. If the intention is to bias, all techniques are only a method to come with an interpretation, right? If the intention is a bias.
No, they are not, I mean, not intentionally. They're just optimistic. Every startup, for example, is very optimistic. Every acquisition is very optimistic. So they put a particular value and then they run this simulation. It will tend towards the more optimistic one, is what I'm asking.
It need not be. The reason is, yes, the kind of inputs you give it, will it impact the simulation? Yes. The answer is not about whether, suppose, for example, you say we are trying to estimate probability of loss or NPV exceeding so much. And you say, because my NPV exceeding is not giving a good number, let me give a very high value to gross margin instead of 20%, 40%. Will my output will be changing? Yes, obviously. Issue is very clear. When as valuers, especially in this group, we are valuers or management who have to take business decisions, because when management says, recently, and when I did one valuation again, and the management was completely in one particular line of business and hugely losses. And they wanted me to value that. And they said that they have changed their strategy this year. And the strategy change is going to propel them into a different league. That was their argument. And therefore, they said that they wanted to value the company because the strategy change is there. But there's no precedence for the strategy change and the performance for that. Similar to a startup, there's no precedence, right? So the past has really been a problem. Whether there are any synergies of the past can be considered, partly yes, majority no. Similar to a startup, no past precedence.
Okay, thanks.
And it is younger, yes. So then I would say there's a high risk. Yeah, you give me a very high margin, I do a different risk. So my questions are very different in such cases. If you say startup, I said that they said that my growth rate will be X percentage. I said, okay, growth rate. Where will you get the growth rate? Production or manpower? They say manpower. I said, fantastic. How many manpower you require? What are the unit economics? How much manpower per person is going to generate sales? They said per person is going to generate so much of sales. I said, how much time it takes for him to generate sales? Give me a number. He said, they will take in per day, they'll convert so much. I said, fantastic. So now I multiply. So I said, you'll need so much manpower. Now, if they need so much manpower, how long you will take to recruit so much manpower? Where is the organization? Where is the staff that you have? Where is the setup that you have it? How much of training you'll have to do for the training for that? And so the questions when you get in, the other cost automatically goes. So that is where management is to answer. It's not a number at the top line. When someone is trying to get into a number, we go to the metrics. Finally, unit economics. If a production is going to tell me, I'll say, what is the capacity maximum? So then they said that I'm going to reinvest. I said, how much the lead, what is the lead time for you to get the machinery? When will you go to give the purchase orders? So the techniques that finally, this methods that we do eventually when you're getting Monte Carlo is essentially we are simulating once there are reasonableness of certain numbers. If you want to, if a management wants to be unreasonable in certain numbers, garbage in, garbage out. Trust I have answered, sir? Or,
Yes, sir. Yes, thank you.
thank you, sir. Any other person, any question? Should I move ahead? So triangular distribution estimation. Has anyone understood how to estimate? So if anyone gives you a triangular distribution of minimum, most likely maximum, generate a cutoff C variable or its check variable or whatever you want to call it. It's a cutoff variable where you are determining whether the random number will lead you to a value between a minimum and the most likely or a most likely and a maximum. That's your checkpoint variable. And random number is generating, giving you the probability between 0 and 1. And given it is 0 and 1, you are going to determine where will it fall. This is how you are going to determine an estimate for a triangular distribution. So imagine if I would have picked up another triangular distribution, just in case I'll go down. I think I picked up for interest rate. Now interest rate, the variable is between, I think, I don't remember, 10, 12, 14, whatever number. So again, I did the same thing. I created a checkpoint, which is basically most likely minus the minimum divided by the maximum minus minimum. I get the range. I get a checkpoint variable. I generate a random number. Once I generate a random number, I have an estimate. And that estimate is essentially telling me, hey, listen, where will I fall? Whether I will fall between a minimum and the most likely, or whether I will fall between the most likely and the maximum. That is how I'm going to generate the interest rate estimate. Agreed? Triangular distribution, how to capture? Any questions?
No.
So sure, right? Sure, I'll move ahead. Just go ahead and practice and you start generating triangular distribution data points. Now I'm telling a discrete non-uniform. Discrete non-uniform, I have a different probabilities for different numbers. So what I did is, in a discrete non-uniform, I have used, this is a cumulative distribution. This is I'll be giving this Excel file, you can use this. This is nothing but a cumulative distribution. So I start with 0%. Okay, that's my 0% is the starting point. Up to 15%, I get 100 rupees. If you go to this probability here, when you see here discrete, up 15% probability is 100. What does it tell me is up to 15%, my sale price is 100. From 15 to 30, so 15 to 45%, that is next 30%, my sale price is 101. From up to 70%, from 45, my sale price is 102. So what I did is that's cumulating. So I cumulated the number. I started with 0, and then that's a mapping number. Up to 15, from 15 to 45, I have 101. From 45 to 70, I have 102. From 70 to 90, I have 103. And above 90, I'll get 104. That is how you plot it here.
So the interpretation of this table here is that the chance that you have a price up to 104 is 90%, correct? That's the way to interpret.
No, 103. Above 90, it is 104. I'm going to use a lookup function, right?
Yeah. So no, I am interpreting from the business point of view, that the likelihood that your price may be up to 104 is 90%.
Yes. Cumulative, yes. Yes. What Mr. Subbaraj is telling is, what does this tell me is, below 104, that is in this case is a discrete number, so 103, 102, 101, there is a 90% chance that the value will be between 100 and 103. That's what he's telling. There's a 90% chance. There's a 70% chance the value will be between 100 and 102. There's a 45% chance that the value will be between 100 and 101. There's a 15% chance that the value will be 100. That's what it says.
Okay. Yeah.
So what I did is, bear with me if someone is not understanding. I'll repeat. I have got a probability specifically that there's a 15% probability that I'll get 100, 30% probability for 101. So I have got a discrete numbers like this. So what I did is I've accumulated that. I've identified where the number would fall in, and I did a lookup function. What did I do a lookup function? In a lookup, I generated a random variable. A random variable generates is between 0 and 1. When a 0 and 1 number gets generated, it gives me a probability. It says 0.745, so 74.5% probability. So what it is saying is, if it is generating a 74.5% probability, where is the number is going to fall? It is between 70 and 90, right? 74.5. Therefore, the number that it has to pick up will be 103. That's the formula this does. I did a lookup function. I generated a random number. A random number is a probability. And once I have a probability, I said, against this probability, look for me between these two columns, C and D. Look for me, approximate to me, against the random number, what is the value I should pick up. So currently, I have not shown a random number separately here. It has picked up 100 for me as an estimate. What it tells me is the random number that got generated was lying between 0% and 15%. If the random number changes, so for example, here I got 108. That means the random number that got generated was between 70% and 90%. How do you generate random number? Just say equal to rand, and it generates me a number. I have no control what number it generates. Whatever number it generates, it will be between 0 and 1. And that's a probability for me. And based on, so the probability is between 0 and 1. So I'm doing a lookup function. So here, if you see here, last one, I got 124. That means my random number that got generated was between 90% and 100%. And therefore, that's my number. Understood? Anyone has questions here? How I generated the estimate for sale price?
So can you put a random number in row 114? Is it possible?
It will change, sir. It will change.
So now it will change. Now it will change.
Okay. What you want is, Excel will be a little slow. You need to bear with me then. What I will do is, I'll do a rand function here. I generate a random number.
And while you do that, a quick question.
Yes, please, sir.
Sorry if this sounds a little fundamental, but if you close the sheet and if you reopen it, then the random number will be generated afresh, right? So every time the model will be new. Is that a problem?
What happens, sir, is essentially there are two things you should understand. Over a period of simulations you have to do, then when you do a simulation, a pattern gets emerged. It won't really matter because once the pattern gets emerged. So you can, that's the reason why we use these distributions, right? Once it follows a distribution and you generate multiple times random numbers, the pattern of 75% confidence level, 80% confidence level, that will not get impacted. That remains the same.
Got
That's
that.
why okay. So what I'm doing is, in the lookup function, I have linked up the formula of random number and I'm making an enter here. It might take a little time, but yes and no, because what I did is for the purpose of modeling for all of us, I did almost on many parameters random variable, and each one I did 10 times. So it will take, but easily. So if you see here, the random number I have linked up the form, it is not there within the lookup function. So we can see the random number and you can see the corresponding number. I hope it will come. No, it's not yet come. Okay, it's come. So now can you see, sir? Someone asked me. The random number that got generated is 0.74. Okay, 0.74 is 74%. That lies between 70 and 90. Therefore, 123 is the outcome.
Got it. So it kind of just identifies what percentage, and from there it tries to look up and see where will my sales price be. Correct? Most likely. And then that it generates that.
No, this is not a most likely part, sir. This is the sale price. Sorry. This is the discrete distribution, sir. So here we have said the probability, we have calculated the probability based on the individual probabilities. I got it. I made a cumulative probability. When you go back to the data point here, we had a 15% probability for a value to be 100. So we said anywhere between 0 to 15, the value will be 100. Then it said 30% probability for the value to be 101. That means we said that between 15 and 45, the value will be 101. Are you with me, sir?
Yeah.
And that's how the random number got generated. Anyone who has, so if you see here, I just shifted my cursor, the random number again got generated. It generated 6.8%, and that 6.8 is between 0 and 15. The value shifted to 120. How many of you are definitely lost, or everyone is on track?
I'm of the view that we have to tabulate trial 1, trial 2, trial 3, like that, some 5, 6 trials. Should we do that? Or should we just keep a screenshot of what we have done and how we are going ahead, that one result?
I share it with you, Shilpa. We have not come this way. So if you see the Monte Carlo sheet, I have tabulated simulations 10,000 times. Okay. Hello.
And
Oh my God. Okay. It's like this. Okay. So I mean, based on the model, you are kind of plotted all the values here and then try to find out the average. Correct? So this is the first step. This is a prelude to that particular model.
This is only one random number, right? This sheet is only one random number. Like this, I have done 10,000 times for each one.
Okay.
In the interest of time, may I suggest that once you give the overview and then we can take the questions.
Yes.
One related practical question: how easy is it to get the customer on board with a mathematical model like this? Can you please throw some light on the challenges that you have faced and how overcome?
Okay. Quickly, one respecting the other gentleman as well here. Quick answer is, please understand, when you do a valuation to satisfy a specific requirement, quickly easy to do it. But when you're talking to Big Four or any big assignments where there's a reasonableness, and this is not only required for valuations, also for business strategy, business decisions actually. So it's a good practice wherever it's possible to do it. In this case, I've done for many scenarios. You can actually limit it to 2 or 3 and do the value modeling. It actually helps you to make reasonable confidence. Even if the client is not asking you to do your own estimates, tomorrow if someone asks you, what are you confident on this value number? You can while you give an absolute number for the purpose of statutory purpose, you are very confident of your numbers with reasonable confidence. Above 50, 60, 70%, you say that I'm confident. And that's the advantage of doing such kind of stuff. I'm not saying for every small things you need to do it, but it will help you to really strengthen the way you are thinking, in the way what impact you are having on the numbers, because your number is determining many strategies, many outcomes.
Thank you.
Unless it's a copy-paste valuation where you have to just give it for a particular purpose, that's a different story. That's not the purpose we are discussing here. Okay, sir. May I go ahead, please? Sorry, sir. I'm very sorry. I'm a little late, but we are trying to finish. So I have discussed the sale price part on a discrete distribution, how I generate a random number. I've still said how I generate a random number. Then I'm getting into the margin. Margin, I said, it's a mean, it's a standard deviation, right? So when it's a mean and a standard deviation, I have a normal distribution. That's a pretty simpler one. So my cursor is taking time to go down. Yes, I've gone down. So what I did is, you have this, I have a mean and a standard deviation. So when you're plotting a distribution in Excel, we use the function called as norm.distribution. Whenever you're using a norm.distribution for a normal distribution or any other distributions, it is going to give you a probability for a particular estimate. So if you want to say my estimate is 20% return, if I plot a norm.distribution, it is going to give me what is the probability for that. 20%. It will give me both options. Exact for 20%, what's the probability? Or it will give me a probability for X less than or equal to 20%. That is what the norm.distribution gives to me. The exact opposite to that is norm.inverse. What does inverse tell me? I will give you a probability. You tell me the estimate. So I don't know whether it is 20%, 80%. I know that at 70% probability, what should be my estimate? So for that, I use a norm.inverse. So I repeat. So if I have a percentage, an estimate known to me at 20%, 30%, 5%, 10%, and I need to know what is the probability of that value coming up, then I do a norm.distribution, normal.distribution, shortcut is norm. In Excel file. But if I know the probability, I said at this probability, what will be the estimate? I will do a norm.inverse. That's what I use here because I'm estimating here. I have used word norm.inverse and I have to give a probability, right? How do I give a probability? I generate a random number again. So I generated a random number. When I generated a random number, I got a probability. For that probability, it has to follow a normal distribution. So I need to give two parameters, a mean and a standard deviation. So I've given the mean and standard deviation. So when I given a mean and a standard deviation, and I've given an inputted a probability by a random number, it gives me an estimate. That estimate follows a normal distribution. I have just used the word zero because I cannot have my gross margin below zero. I just said, okay, let me make it maximum of 0, this. So that in case my normal distribution gives me a negative number, I don't want to take a negative number. I put a 0 as the condition.
So the D82, D83 in that formula indicates your mean and standard deviation. No?
Yes, D82, D82, 83 are mean.
So the mean and standard deviation. Okay. Okay.
This is mean and this is standard deviation.
Okay, yeah, got it.
So we have seen in triangular distribution, when we have mean, most likely minimum, maximum, we have generated a random number. We have a bigger formula there and we calculated what will be the value. In a sale price, we had a discrete data points. We have used a method of lookup function, generated a random variable corresponding to the probability. We generated an estimate. For a gross margin, we have said it's a normal distribution. So we have to use norm.inverse function to get an estimate for a gross margin. Sales general selling general administrative expenses, SGA, that we stated here as lower value and higher value, but uniform. We said that it's a uniform distribution. Uniform distribution means it has a uniform probability. That's a simplistic way of doing it. So what you need to do is you generate you take the minimum. Minimum was 8%. Okay, that's a lower end. It cannot go below 8%, right? Then what I did is I generated a random variable. The random variable will be 0 and 1. So I picked up a random variable. I multiplied by the difference between the maximum and the minimum. Now, just visualize this, for example, maximum minus minimum. My maximum was 10%, minimum was 8%, right? The difference was 2%. Assuming the random number gets generated as 1. That is, so 1 into the difference was 2% is 2. The 8 plus 2 is 10. That means the maximum this distribution will have is the maximum value. If the random number is 0, for example, then 0 into that number, 2% is 0. Therefore, minimum plus 0 is minimum. So therefore, my values will fall between 8 and 10 all the time. And this is how I generate. If the data distribution is uniform data distribution, I say minimum plus random number you generate into the delta of the max and the minimum for a uniform distribution. And you keep there. So what does the random number do? It generates. And every time it generates, whatever probability, you just multiply and that's the value for you. Why are we doing this again? That question we have to answer. Because we don't know whether it's 8% or 8.2 or 8.5. We wanted to simulate it. And that's exactly what we're doing here. This one is delta reinvestment to delta sale. So here, if you see here, this I have given it only for the purpose of explaining other option. I have given you discrete distribution. but they are almost uniform. If you see here, almost 19.95. There's another function called rand between. So we have been using rand, so I thought I'll use the rand between function. What does rand between do? Rand between always gives the numbers between the minimum and the max. We need to give a lower value and the higher value. So what you say is rand between say 100 and 120. So it will always give numbers between 100 and 120 when you are simulating it, random numbers. Always, because you're given a lower value and you're given a higher value. So what I said is, if I know my distribution is going to follow between the above 5 numbers and it's almost uniform, which is 19.85 and 20.15. I have said the lower value is 19.85, higher value is 20.15. Let me generate a rand between. Now, please understand here, we don't want, we wanted a rand between always gives you integers. So but we have 19.85, the decimal percentage, 20.15, the decimal percentage. So what I did is I multiplied by a number and which makes it an integer. And I generated it between those two integers and again divided by that number to get back my decimal number. So it's just another way to generate a random number, especially if you're integers, you can use rand between. If it's a decimal number, but you know very well it will fall between these two ranges, then you can use rand between, but the decimal you convert into an integer and then make again a decimal after the random number got generated. I hope no questions on this, right?
Only one quick question. Is there any merit in using the same random variable across a column instead of using multiple random variables? Is there any merit or demerit of the two? I mean, in the first instance, if you generate a random number, then does it make sense to use the same random number across all the rows? Or
no.
Because here we are generating a random number at each row every time.
Yes.
Is that a better distribution or?
Yes, because year 1, year 2 are different, right? Year 2 follows a different distribution. So see, random number, whether you're using multiple years or something, the moment you click it, every time it generates a random number, right? Distribution is the same. Only thing is if the lower bound and upper bound are varying, then it makes sense. It will have a different. You can use the same random. Random number is a random number. For example, what a question, I generate one random variable, whatever it is. I've said that for each year, I have a different lower bound and upper bound. I can use the same random value and apply it accordingly.
No, not across columns, not across columns, across rows. For example, here in 117, you've got gross margin to sales and SGA % to sales. We are generating two random variables there independently. Is there a merit in using the same random variable or is there no merit?
It has no sanctity. That's just explanation of it. You can just generate one random variable and apply it to everyone.
Got it. And it won't dilute the simulation in any way.
Why will the random number is not diluting it. Random number is only giving you a probability between 0 and 1. Nothing else it is doing. Random number is only giving you a probability that you are applying based on that probability for your data points. For example, in a sale price, I have to use that output in this fashion. For a gross margin, I have to use that fashion. You are doing that. Random number is not getting impacted.
I got that, but maybe my question wasn't clear. If you look at D117,
okay,
you are using a rand.
Yes.
Actually, yeah. And then even in 119 or similar row, you are using a R&D, correct? Rand.
Correct.
Is there a merit in both these rands being the same, or is there a demerit?
There's no merit or demerit. It has no impact, I'm saying.
It has no impact. Okay, thank you.
It has absolutely no impact. I'm only saying that we rather use one random variable and apply for all. No issues.
Thank you.
It has no worries. Okay. Because what we are doing is we are analyzing the data distribution. So random number. So, okay, I'll tell you one example, very interesting one, since you're asking this. The same random number that you have used for, say, gross margin upon sales, and you have said normal distribution. The same random number you have used for the next SGA % sale, where you said it's a uniform distribution. When you actually plot the graph that you get it for the sales general administration, that will be uniform in nature, that data points. Whereas for normal distribution, when you plot the graph, that will have a normal graph.
Got it. Thank you.
Oh my God, it's 9:57. Working capital to sales.
Ganesh sir, could you please show the conclusion, like how you have arrived at a share price of 238?
Okay. Okay, almost done then. I'm shifting. So I hope you have understood how we calculated we have shown all distribution. After that, it's a repetition. So we have shown uniform discrete, random, uniform continuous. We have shown triangular. We have shown discrete non-uniform. We have shown normal distribution. How to estimate a number based on the random number.
Yes, it has been very well explained, very informative and useful. It would be further useful if we can get the Excel sheet so that we do not need to re-put the formulas. From the formulas point of view.
Excel will be given, sir. Excel will be given, sir. Confirm.
Thank you so much. Thanks a lot. It's very well explained, and I'm really amazed and advocate, explaining statistics.
So nice of you, sir. Thank you, sir. Thank you. Much appreciated. So here, this is a Excel tool, sir. Okay. Whatever the random variables we have generated there, I started putting it here. It's a reference of that particular sheet. So if you see here, the sale price, sale volume, gross margin, sales and administrative expenses, what we got in sheet 1, I actually plotted here. All right. Now I need to generate it 10,000 times. There's a function called data analysis where I don't need to, if I copy this formula 10,000 times, computer will hang. Don't do that. Never ever copy that. It will be a nightmare because every time random number 10 times. So what we need to do is, in Excel, there's an interesting function called data analysis. Some of you will know who are experts in Excel than me. And for the people who don't know, probably I'll try to share. I don't know how do I get it. Okay. Here, can you see my screen? You can see the screen, right? This is the data. And there is a what if analysis. Within what if analysis, there's something called as data table. Can you see this, everyone?
Data table hasn't popped up yet, but yes, the concept, I think most of us should. I
don't. Yeah.
Should I skip it? Should I skip it?
I generally use goal seek and all those are those options are under what if analysis.
No, data table is with the braces.
Yeah. No, so in that same drop down, you find goal seek also. That's what I'm saying.
Yeah. Should I skip data table? Everyone is familiar with it then? I don't need to explain that, right?
Under what if analysis, sir?
Oh, it is under what if analysis. What you are doing is you are mimicking this formula for Excel and you are actually pasting it 10,000 times. The advantage is therefore it will come as table. If you see this always this cell, it will show it as table, 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 and all this. So it actually is it's very fast. Otherwise, it will be a nightmare. And you cannot delete individual cell. If you have to delete the table again and recreate the table. And using data table is the right way to do it the fastest in the simulations. I'm assuming since you are saying that you are all familiar with it, I'm not explaining the data table concept. So I got the sales growth. I got the sales price. I got the gross margin. I got the SGA value. I got delta capex. I got working capital. I got interest rate. I got contingent liability. For all the simulations. You just simulated, right? 10,000 times. Then therefore what I did is, okay, fine. Each simulation, please understand. You remember in my first one sheet, I said in Monte Carlo, this is my first trial. In my first trial, this is my growth for year 1, year 2, year 3. This is my sale price for year 1, year 2, year 3. This is my gross margin. All these numbers for this is one trial, this complete set. Against this complete set, this is my complete revenue. This is my gross profit. This is my SG&A. This is my EBITDA. This is my depreciation. And this is my interest. This is my EBT. This is my tax. This is my profit after tax. This is my reinvestment capital expenditure. This is my working capital. This is my change in working capital. This is my delta debit debt. And therefore, this is my contingent liability. In contingent liability, I applied a small formula here. What I said is, if I have incurred a contingent liability in year 1, based on a simulation. The simulation will give me in year 2 also because of probability. But in reality, I will not incur a contingent liability twice, right? So I said, if I have incurred in liability year 1, I will not have any more liability in year 2. If I have incurred in liability year 2, happens in 5th year, in 5th year. That is how I have calculated contingent liability and I have calculated the free cash flow to the firm. This is all of us know how to calculate free cash flow. So this is for first trial, one trial. Free cash flow to the firm I've calculated for one trial. Like this is my second trial. This is my third trial. This is my fourth trial. This is my fifth trial. I have done 10,000 trials for this. And given this 10,000 trials, I also done a simulation for terminal value, because my terminal value I've done using a sales multiple. My sales multiple is changing year on year. Therefore, for each trial, therefore my terminal value will change for each input trial. So I have 10,000 terminal values. So this terminal value is applicable for this free cash flow. This terminal value is applicable for this free cash flow. What you cannot do is the year 5 sales growth, you cannot mix it with the year 1 growth. It actually is a random number, but ideally you should not do that for a trial purpose. So in other words, what we are doing actually, what you would have done one time as a point estimate, I've done 10,000 times. And therefore I've calculated the present value. And the present value also changed for me because my interest rate was changing, because I put interest rate as uncertainty. If interest rate is changing, my WACC is changing. Because my WACC is changing, I have to estimate WACC for each year, and therefore I did a present value thereafter using WACC, and therefore I calculated the price value and then the equity value. And once I got the equity value, I calculated the per share value as well for each year, for each trial. And then once I got this, this is for a concept definition. I have ordered all my outcomes. This is if for free cash flow, 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 year 1. My random number does not generate in one particular pattern. It follows a particular distribution. So it generates me random values. But what I said is, give it to me in an order of ascending order. So what I said is, lowest to highest, you put me in the free cash flows for year 1. Lowest to highest, you put me in the highest. What are we telling from lowest to highest? Imagine a normal distribution. When the curve is like this, my probability is 0, my probability is 1. So it's a continuous. So when I say at a 70% probability, that means this entire cash flow, this area, all these are part of me. 70th year percentage, I'll have this is the cash flow after ascending order. Like that I move. So once I put in ascending order, I know exactly if the value at 100th row, this is the 10,000 trials, right? The value at 1000th row is a 10% confidence. Value at 9000th row is a 90% confidence value. Value at 5000th row is a 50% confidence value. What I did is I just ordered in ascending order, and I plotted this. Now I know what is the minimum value, what is the maximum value, what is the mean, and what is the 90% confidence or the 10% confidence. I have arranged it. Because I have arranged in an order, it follows from 0 to 1, because in the actual simulations, the random number is random. I don't know whether the higher value will come in the beginning or later. I don't have control. So I arranged it in a particular fashion. And then I said, what's my confidence where the number is falling? Then I go back here. I plotted here saying that year 0, this is my stock price. This is my free cash flows. My year was, this is my year 0, what I did, my manual estimate or point estimate. Then I said, these are my maximum values. Year 1, year 2, year 3, year 4, year 5. This is my maximum value. Don't guys, there's a formula error or something here. Okay, just looking at something else. You need to see. This is my minimum value. Year 1, year 2, year 3, year 4, year 5. This is my 90% confidence. This is my mean. This is my 10% confidence. This is my minimum. So I have plotted the cash flows year on year, the maximum value, the minimum value, 90%. If you want, if the management says, tell me the 75% confidence level, I just have to go to this particular simulation sheet, identify the 7,500th row. That's my 75% confidence level. Now, when someone was asking me, if everything is most likely, where will I fall? I can actually tell with what confidence where I'm falling. And here, it's not one variable. I have taken different variables which can follow different distributions. I've calculated an NPV, and that NPV is what I'm concerned about, consolidated with various values. And I said, if you see with 90% confidence exceeding 350, I have only 0.2%. So I am 99.8% sure that it will not cross 350. While my maximum is 367, I'm reasonably confident 0.2% is only the probability that I will get more than 350 value in NPV. Whereas I am reasonably confident with 90% because 10% value is a 290. What I'm saying is 290, I will definitely get it for sure. That's the minimum. Minimum is 260. I cannot go below 260. So I'm actually started telling you the range where we are falling. So that management they say, oh, listen, I don't want to go below 280. Oh, this tells it can go below 260. 260 is the minimum. Then we can say 280 falls at what level? And those are the business decisions when people are taking, where it is falling. And because here we have done 10,000 times, we can do 100,000, we can do 1,000 times, but the more the better, but you need to have a reasonable number for you to start telling in where will it fall with confidence. Because certain times business decisions are very important. I'll give an example to you where it is important. For example, in a quality testing, suppose if you say that you cannot get more than 5% errors, that means there's a problem, right? 5% is a small number. So we cannot have so less because that has a different impact of reputation of the company, the brand name. It has other ramifications. So we need to know, given this, suppose if it comes to us that the probability that it can impact more than 5%, then there has to be more expenditure on the quality, manpower, everything. I need to do that so that my risk does not fall below 5% on quality. And that's exactly what we tell. And when someone asks me how the data shifts for each one, what we did a simulation, 10,000 simulations we did, we had, this is the minimum that we had in a sale quantity, this is the maximum, this is the median, and this is it. Yes, if someone says that I'm going to skew the most likely, then the most likely will change. But then this minimum maximum will change. And that is how we plotted all this. And we are able to tell where is the value. So when we are giving a value, NPV is a value that we want to give it. Now we can tell if the value is going below confidence level of 50%, 40%, we don't want to give that number. We said that's unlikely given these estimates. We cannot give you that value. Either you have to improve on your estimates, you prove that you can improve your estimates, or this is some other value I'm going to give it. I'm reasonably confident. For a statutory person, sorry, sir.
What is in the column simple?
Simple is the base average. Simple is the base average. What we just did, point estimates. Okay. Starting, that's a simple. Basically, it's an existing sheet, so that's a wording. It's a baseline. Simple is a baseline.
Okay, and what would have been the value had we not done these simulations in the normal traditional manner?
According to this, it is 148.6.
On the base data itself.
Yeah. So okay. it is. I've just taken that numbers. This is simple linked up sheet. I'm assuming all linked up are correct. Yes, I think they are, and therefore that is the number.
Sir, one question. Something on that independence required.
Super. 1 second. So before I miss that, see, please understand. These are hypothetical numbers I was throwing to create a template. Okay. Kindly note when you do it with reasonably right numbers everywhere, then the interpretation is. Don't prefer saying that simple will always be so far away from the other numbers. That's not correct. I hope I answered that, Sanjay.
Yeah. Yes. My question was about that. The requirement that variable should be independent. Okay.
Yes.
When you look distribute now, for example, here sales value is not independent. It will depend on sales quantity and sales price.
Yes, sales value is dependent. So therefore I have done the simulation for sales quantity and sale price. Those are independent.
Okay. But can you just show me that tab also? You have done simulation for gross margin and stuff like that also, right? Yeah. But again, gross margin is not an independent number. it'll be dependent on sales price and cost. So,
Correct. See what
so
happens.
has the independence criteria been met for gross margin is the question. It's not an independent number, right?
Yeah, you remember very beginning I said, in practice, independence and ideally identical distribution is a requirement for law of large numbers, right?
Okay.
But I also said weak law of large numbers, right?
Okay.
That's where it means essentially it still tends to the averages from that perspective.
Okay, so effectively what you're saying is for doing this simulation, independence as a requirement is actually not there.
Yeah, see, in practice, mostly we'll always struggle on independence, any which ways. Let me be honest. We'll struggle on independence. But somewhere, that's the reason why I was introducing that theoretical concept.
And one more question. See the selection of the distributions. Okay.
Yeah.
Some are selected triangles, some are selected normals, right? How sensitive is the output of this entire exercise to the choice of those distributions?
It is.
And are there any guidelines? Are there any guidelines on when to follow which distribution, or that's where the statistical expertise comes into play?
Yeah, actually it is. In practice, if ideally the best distribution, that's why I said that's a different study altogether. And some of the software guys also say, tools say that we'll help you best fit and all that stuff. Okay.
Okay.
But the question is, there is one study says that, I think, did I miss that in the theory, where it says that while the distributions may not be a particular distribution, the means eventually tend towards the normal distribution. There's a study on that. If you see even here, after we plot eventually the NPV, it followed a normal distribution, right? Okay. So that is something. So when I was doing a lot of reading, business decisions, business people, triangular distribution is the easier one. People are using it. And that's comfortable and normal distribution. These are the standard ones which are using it. Yes, when you're getting into the high level, probably astronomical or some other spaces, probably you may need much more clarity on specific distribution. But you are reasonably good to go if you use these 3-4 distributions, what I stated, given the data points. And if you are reasonably concerned that it is significantly skewing, then it's a little bit of trial and error. You change it and see whether it's any major impact. Because the theorem of the eventual tendency is towards the normal distribution, that will apply in my view when you do a large number of.
Okay. So supposing some of us were to try to do this entire exercise for the first time.
Yeah.
Okay. How much time do you think it will take? 4 days, 5 days, 1 week, 1 month?
Okay. This sheet is being given, right? Okay. Use this sheet. Don't try to do it. 2-3 times reading of the sheet.
Okay. Okay.
Close the sheet again. Again, next day, come back and read the sheet. That will help you to familiarize what we are doing. And then you start playing around. That's a recommendation. And see, Monte Carlo is only a simulation technique, right? It's just helping you to simulate, saying that use different data distributions and what one person with one thought, instead of one thought, if you're doing 10,000 thoughts with a particular distribution, where will this fall for a business decisions? So a lot of business decisions we can take by simulating so that we can come with numbers.
Great.
Any other questions? Can I stop the screen? That's all from my side. I know it's 10:15.
I think it's too late to take up questions. Still, any participant would like to?
Yeah, I had one question. Ganesh, when we are talking, this is a level of confidence. So when you spoke that this is the level of confidence that we are talking when we get a number. What is the interpretation? What are we saying actually to the client? You said that with we have got a level of confidence of let's say 40%, and then we go back to the client and say, no, this estimate is not okay. Give me another estimate, correct? So when we are doing, how are we interpreting level of confidence versus what we are trying to say? Okay. I didn't get that part.
Okay, this is my favorite rather. It's a business cause than a valuer's call, but I'll give a perspective here. What happens is the management is saying that these are my numbers because the numbers are plotted at a very high level, right? Okay. Now they are planning to bring in an ESOP policy. So when they want to bring in an ESOP policy, they also want to not let it go. They don't want it to let it go so easily. And they want to ensure the capital structure is not disturbed significantly, but also it's not look so impossible that no one comes in. this is a call. They can actually tell reasonably with 90% confidence where will the sales or where will the profitability be. Number one. So you are actually giving them the confidence where the numbers will fall. It's not 100% always. So if they say, okay, if I'm 75% confidence, I'll go for it. That's the decision making will happen here. I'll give another example here. So for example, the management says, these are my years of projections. Tell me what kind of employment I have to invest in employment and infrastructure for achieving these sales. I want to do that provided I'm reasonably confident of doing it. Then you again look at the confidence level and say, like, listen, this is the confidence level you'll achieve this number, given your projections. Okay, that means that investment is valid. If my confidence level is less, my investments are shifted, because if I have to invest, I have to start my work for raising funds or loan or whatever much earlier. That gives me lead time. Valuations. If you are saying that this is the confidence level, that then the management will say, how will I go to the investor with these estimates? Either I change my business strategy, either I change my projections, either I introduce something else, which will give confidence to the investor. These are my numbers. And when you're going to talk to the investors, you talk with reasonable confidence. This, I've simulated this. These are my numbers. With this confidence, I'm telling you, I'll achieve these numbers. To the investors. To the employees, I said. To the investors, I said. For the management, for the decision on the capital structure, I said. If you're introducing a new product, you're a marketing agency, you need a budget, you need to plan. You can actually tell with what confidence this new product is going to generate me sales. In other words, what we are saying is, given the probabilities that you're talking about, this is the sales. Either your probability has to increase or something else has to, your estimates have to come down. Then you suddenly increase the probability, as one of our dear colleagues has said that, and that's correct. Then I say, okay, what is the basis of this probability? Don't fool yourself, because finally it's a business call, right? It's not always taking money from some investor. Then you go back and say, am I going to get that number? What is the basis of it? So the simulation actually what it is doing is, instead of one person putting one number and looking at an outcome and taking a business decision, you are actually taking a 10,000 people decision, which follows a particular pattern and then making a call.
It's essentially saying that instead of gut feel, you're saying that now that gut feel is converted into 10,000 decisions or numbers, and therefore the level of confidence could be high or low, whether that can be achieved or not. Correct?
Exactly.
That's essentially what you're saying.
Yeah, if you see the very first slide, that's exactly what it says. Earlier, we used to have point estimates, single point, right?
Single point, yeah.
Now we are taking, no, you have a computer power is there. So let me do a pattern analysis.
So if I say that I have got 75% confidence that I'll hit X number as a sales, correct? Now that, whether that is true or not, can be tested with this model.
Yeah,
yes,
absolutely.
whether you'll hit it or not, correct? And that what is the level of confidence that you'll hit it at? So let's say the level of confidence is, let's say, only 50%, correct? Then we say that it doesn't meet the criteria. You pare down your sales, or some assumptions has to be tweaked.
It's a business decision, right? So, fine. See, we are independent people who are professionals applying techniques. The management has to call, and that's the reason why it is important that when business decisions are taken, okay, in practice, everyone says, "Mera gut feel hai." Gut feel, you can take it as long as it's your own money. You want to put the money in the dustbin? No worries. Please be my guest. If you're playing with others' money, and others' money includes banks' money, investors' money, gut feel has to be calmed down.
Yeah. I have one small request.
Thank you.
Sharing the worksheet, right?
Yeah, I'm sharing everything, sir.
Yeah. So one request is, along with the worksheet, could you also have a brief narration on how to read that worksheet, in the sense that, so you mentioned about the pattern change, pattern and all that. So if there's a small narration that, okay, this variable changes or this random number changes, this is how the pattern changes, and I'm not talking about a very elaborate thing, for us to see how dynamically it is changing.
Okay.
And the value, if it can be done. Okay, very useful session, but I am not sure I'll be able to absorb a worksheet with 10,000 lines or whatever it is. So I needed that.
That's appreciated, sir. My recommendation is 10,000 is just a number. That's a simulated sheet. The main sheet was the fact sheet. You don't need to go anywhere else. Just see
But
the.
can I see the pattern changes is my question. You kept referring that you will see when by doing this simulation, you see the pattern. So that's what I wanted to look at.
The pattern is okay. I'm not sure the question. The pattern is essentially when I have decided that it will be a triangular distribution, normal distribution, I've defined it. Then the fact sheet has a formula which actually calculates an estimate. That estimates all are simulated in the other sheet. Whatever pattern you decided in the fact sheet, the simulated sheet, if you were to plot, it will eventually follow that particular distribution. That's all I was saying. Nevertheless, I'll see if I can add a sheet. I'll send it, and I'm always there. Whatever inputs I can give it, what best I know, I'll share.
Maybe what we can do, Subbarao, Shilpa,
Yeah.
we are planning for an offline session, a 3-day or 2-day session in January or something, right?
Okay.
Maybe there a half-day session to, actually work through and maybe create a kind of a sheet for members. I don't know, maybe you can plan something like that, right? Maybe the scenario can be agreed upon in advance, and maybe Mr. Ganesh Remani can maybe maybe the exact same sheet that he produced here, so that what Naren was saying a short while ago.
I got your point. It's like workshop.
That might be useful for people to and people get their laptops along and any software or any stuff there to install, let them come and let everybody do a hands-on session with Advocate Ganesh leading and the people following, and that way maybe it will be a deep dive into Monte Carlo, maybe a half-day session like that or something. Or what do you say?
We'll explore that option.
Yeah.
On behalf of Bangalore Valuers Association, I request Mr. Subbarao to formally convey a vote of thanks for today's speaker.
Great. Great, sir. I think I thoroughly enjoyed this session. Honestly, it may for the last 1.5 years, I've made several attempts to understand, tame this animal called Monte Carlo simulation many times. Looking at YouTube videos, downloading some Excel sheets. One of my nephews had an expert in Monte Carlo simulation in terms of MS in the US, but somehow I could not move forward. I think a session like this was most useful, so that a topic like this, Monte Carlo simulation, notwithstanding the fact that I'm a graduate in economics and statistics and maths, maybe some 25 years ago, 30 years ago, but still it was a bit intimidating. And I think the first initial session like this would be the perfect, I would say, stage to get started on my quest to tame this Monte Carlo simulation animal a little more. And but as I said earlier, the way I look at it is, this could be just the beginning. It would be extremely useful for some of the members who are interested in deploying this technique in their valuation work to perhaps create some kind of a predefined scenario and do this hands-on. Definitely, I see a lot of inertia I was able to overcome by this sessions. I was very patiently spending time and going through this, and I'm 100% sure every person who has attended this session would find this extremely useful to at least some ghosts that are there in your mind, as the speaker Ganesh mentioned earlier. Like, if you want to, like Gabbar Singh, people would say that if you want to sleep, you would threaten kids. Like that, this Monte Carlo simulation, some kind of a Gabbar Singh, and at the end of the session, we definitely look like I don't know what equivalent we'll say out of a Sholay character, whether the Gabbar Singh has become a Basanti or I don't know, but but definitely the goal would be to demystify Monte Carlo simulation to a lot of practitioners, and I think there's a great, excellent first step towards demystifying that. And somebody is posting it 3 hours, but I never realized it was 3 hours. Okay, so looking forward to push ahead my own further research and understanding about the Monte Carlo, and this was the perfect platform for that. Thanks a lot, Ganesh sir, and thanks a lot BVA for organizing this session. I don't know how much time it would have taken for you to prepare for this. It would have taken donkeys years to even come to a stage where you can create the. I mean, I was noticing the quality of the slide, because statistics is an extremely broad thing, and the main challenge for anybody would be to what to put in the slide, make the slides to create the content of a presentation and make it prevent it from running amok and going all over the place, right? To decide what to put and what not to put, that itself is a huge decision, given the background of our members, and one can very easily simply go off the handle and include anything and everything, and the interest of the audience would very easily get would start wandering. So I think the multiple challenges I would have seen here, and I was observing the PPT from that point of view also. So 100 hats off. It is very very difficult balancing act to achieve to create a PPT for a session of this kind. And I think the idea of the amount of effort that we put in to create a session like this was itself extremely scary. So thank you very much, and I enjoyed it thoroughly. I'm sure all the people, and I noticed that we reached a peak of 67 people during the session, and that indicates the intent, the extent to which people are interested in learning this technique. And Subbarao, Shilpa, if you want for our January proposed session, let's do something. Let's take the next step and demystify this a little further for our members, is what my suggestion would be. Okay.
Yeah, we'll explore.
Thanks a lot, Advocate
Thank you so much,
Ganesh Remani. It was brilliant session.
Thank you so much.
As a token of appreciation on behalf of Bangalore Valuers Association, I hope all of you can see my screen.
Yes, we can.
Yes, we can.
Can you see the momentum?
Yeah.
Yeah, on behalf of Bangalore Valuers Association, a small token of gratitude for Mr. Ganesh Ramani. Sir, we'll be couriering this memento to you. It's an honor that you are here with us and sharing your vast knowledge, and try to you have given your best. Now it is for us to unravel the mysteries on our own. Thank you so much, and please share the PPT and the Excel.
We'll do that. Thank you so much.
Lovely memento, Shilpa. Thanks for whosoever other members who did the groundwork for selecting this. Behind the scenes, silent workers. Hats off to those people also. Lovely memento for a lovely session.
Thank you, sir.
Okay, bye all. Happy
Thank you.
weekend.
Thanks, everyone.